today and tomorrow maybe we will be discussing more about the modeling. So today we have three plenary talks in the morning session. One is by Dr. Prabir Patra. Prabir Patra is, as you know, everybody knows now. Since it's for younger colleagues, I just introduce one or two words about him. As he is a senior scientist at the Department of Environmental and Geochemical Cycle of JAMSTEC, and is Japan Agency for Marine and Earth Science Technology. And he is one of the key person who began the JAMSTEC's that atmospheric chemistry transfer model. And he is also actively involved in the transform transfer model intercomparison project, as well as our greenhouse. He is one of the main pillar of this greenhouse workshop organized by this IATM. And at present, he has the main, his designation is that he is the lead author of the IPCC AR6 document, and the essence he will be presenting now. And he has more than 260 publications, and I think more than in Google citation is close to more than 20,000. I think. So over to Dr. Praveen, please.
Yeah, thank you, Siji Kumar. And yeah, so today I decided to talk about some of the essence of the IPCC AR6, basically chapter 5, where I contributed. Because these chapters are very big, the content is very big, the size is not so big, but because we are actually kind of reviewing something like 10,000 papers and put into this kind of small report, and there are about each chapter has like two lead authors, coordinating lead authors, like Krishnan was one of them in another chapter, and we have like about 10 to 15 lead authors in chapters, who actually review thousands of papers and try to make a summary out of it. So not everything I can cover, even for our own chapter, but I will try to give you some idea about what has been done by us, and also linking to the bigger picture of IPCC in this AR6 Working Group 1 report, which is the physical science basis. And I, of course, will try to focus on the greenhouse gases and their emissions and removals, sinks, and rigidity for sinks to some extent. And so before I forget to do the thing for our meetings, these workshops. So first workshop was in IITM Pune, as you have all heard. And we actually, at that time I did not have a mobile camera so good so that I could take pictures. So I have very few pictures. And you can also see that there are actually boards where the equations of inverse modeling were solved, and it was given, the course was given by none other than B.K. Gaur, and many of you may know him. He's a really, really prominent scientist in India, I think still involved in many policy making in the highest level. And so the topic, what I mean to say, the topic is so important, even the highest class people come to this kind of initiative. And then the second one was in ISR Kolkata, and the difference from ISR Kolkata, we had a field trip as a longer period. There was a field trip, and there are more people and many more things. Like also there are funds to take people on the Sundarban trip and all the things, and show them the Punyas Lokan showed them how to do sampling, and his colleagues and did a lot of work to make this happen in a way that people learned a lot. And of course there are lecturers from all over the place, and they also had some sort of a different outings, and so people enjoy these things when in person, which we will miss this year. So that's why I was asking on the first day whether we are going for dinner now. But anyway, coming back to this IPCC report, is that you might have seen this diagram already, so which basically shows how temperature has changed over the last 2000 years, for example, 2020 years in this case on the left-hand panel. And so on the right-hand panel is showing how the temperature has changed in this time, but for a short period of time. And you should also maybe remember that 1850 is the kind of a base period of IPCC AR6. Before we are talking about pre-industrial to 1750, the pre-industrial time still remains 1750. But in this assessment, somehow we changed that in the report baseline to be 1850 to 1900. That's mainly because in this period we have direct observations of temperature. So if you go beyond 1850 and the time before that, so you have to reconstruct the global surface air temperature. You cannot really have observations all over the globe, so you have to reconstruct some part. So this is why the change in the baseline of the IPCC AR6, and it will be like in 1850 to 1900. And this is again, you can see that it's flat period. So this is baseline, and then that how the temperature changed with time. And again, the black line here is the observed, and the simulated line are shown as a brown line, and that includes natural and human activities in the models. So different kind of models. There are like emulator models, there are Earth system models, there are other estimations. So all sorts of things goes into this calculation. And then this is what is called model. So the spread is big, but still the mean temperature change has been very well followed by the models. And you can also separate the natural and anthropogenic. This is also the biggest point in this IPCC, because if you do not know what is happening naturally and what is happening because of the human activities, we cannot take decisions on the, for example, how to improve the situation from what is happening right now, the global warming. And so the global warming obviously has many effects. This has been, I think all of you know this, but I still to reiterate what has been discussed in year 6 is that there will be extreme heat and more frequent and more intense. Some of them are already observed, and also the predictions say the same thing, like it will be also more in the future. So heavy rainfall, it will be more frequent and more intense, and drought, you can see that it's some region. And you know that the drought is not uniform because there will be patterns of change in rainfall, and with the increase in temperature, we also expect that there will be more evapotranspirations and all sorts of things, and the circulation changing. So it's not be all will not be uniform, but there will be some places more, some places less, and it can be different in opposite direction in some areas. So more fires, and you actually see this happening in many of the regions of the earth, and it's controlled or uncontrolled, and so it's really a hazard for human living. And then in the ocean, so I also have one slide to show that when the CO2 goes into the ocean, it actually acidify the ocean, and then because of the warming of this warming heat goes into the ocean, and it also loses oxygen because the solubility changes and everything else, and the biochemistry also changes. And so, as I said in the first slide, that the temperature is changed. If you just see the 1950 to 1900 and to the most recent decade with this time period, you can see that the temperature has changed about 1.06 degrees centigrade in the past 120 years, for example. And then if you do the other model simulations, which you do in this case, and you can come with another bar here on the middle, which is basically say that how much is due to the human influences. And then you can further subdivide them into different constituents like CO2, methane, N2O, and halogen-related species and other things. So we don't discuss this box and the species in the box too much in this case. We basically discuss first one, CO2, and then methane, and then very little bit of nitrous oxide. And you can see that so if you add them all the main 3 greenhouse gases, the warming will be much bigger, and some part of this is basically reduced because of the aerosols have a masking effect of the sunlight, and then you are actually cooling the Earth's surface because of the blanket on the top of your atmosphere. And so with that, I think I'll move to the next slide just to show you that. And then, I mean, it's also like a starting point for us to think, how can you establish firmly that these changes in greenhouse gases are happening due to the human activities? And to that, of course, we just look at the historical again from last 2000 years, because again, we have a more confidence in these observations. We can have a high resolution of the measurements. I mean, you might have seen the data going back to like a 2 billion years back, or several hundred million years ago back. But then all reconstructed, and they reconstructed from the ice cores, air bubble trapped in the ice cores. So we don't have the time resolution to do the science we need to do to establish these facts. So there are some reasons why we basically try to focus on the more and more recent times where we have more accurate observations. And as you know that, yeah, so actually humans are very well there in this time, and then the measurements show that it's quite stable and not changing so much. The CO2 concentration, also methane concentration, also N2O concentration, they did not change until about let's say 1750, which basically we have like a pre-industrial time, and then it has, you can see the acceleration in the concentration change because of the industrial revolution, and then the agricultural revolutions, and all the things happens and to meet the human demand for food, for luxury, and everything else. And so basically the values were like like this in the past, and if you see the present values, they're all actually accelerated in terms of concentration changes. And so again, I said we focus on more and more recent times, depending on what we want to analyze. In this case, I am showing that the results, time series results of CO2 and the associated parameters when we want to study the CO2 carbon cycle, CO2 or carbon cycle. And this is starting from 1957-58, because this is when the Dave Keeling of Scripps started the measurements up at Mauna Loa in Hawaii, and first in South Pole and then Mauna Loa in Hawaii. And this time the series is going on for a long time, and you can see that that's actually very nice in the seasonal cycle. There is a tendency, and everything is like recorded very, very precisely. Like we are talking about 0.1 ppm precision. We are talking about that. And then the GOSET has come in from this somewhere around here, 2009. So you cannot see the plot, but you can maybe see a little bit here the GOSET data, which is green. And so this is, they are all like adding a layer to our understanding. So every time the new measurements comes in and the new parameters comes in, they add it. And to explain you this, what is also shown in the red line here is the Mauna Loa minus South Pole difference. Mauna Loa is in Hawaii, Northern Hemisphere. So it is kind of in the mountain top, which is about 3.6 kilometers, which means that actually it is seeing kind of a Northern Hemispheric mean concentration. And then you have South Pole, which is like a far away from all the activities from fossil fuels, which is shown in the map on the right. And so because you have a lot of emissions here, and then there is winds flowing mostly the zonal direction, and there is some mixing, and by mixing also it of course go to southern hemisphere, but that process is much slower. It takes about 1 year. So then that difference, so how much you emit in the northern hemisphere and how much you emit in the southern hemisphere, and then the transport time scale, we can actually calculate this Mauna Loa minus South Pole gradient difference. And that also tells that, and this because this is northern to southern hemisphere, so depending on how fast the emission increase in one hemisphere relative to other, it gives you this trend. For example, southern hemisphere increase faster, then you will have to have a reverse gradient like that. Or if they say that they're equal, you will not see any gradient. Gradient will come to 0, because if both hemispheres emit the same amount of CO2 to the atmosphere. So these just basically tell that, okay, northern hemisphere is the highest emissions for CO2. Then you can also see that in the seasonal cycle, we can in this every time we see these eagles. And from there, you can also use our biospheric models and the biosphere, which is many people have actually very well tracked the gross primary productivity on the land biosphere, for example, which actually dominates the seasonal cycle, and how it changes in the season. In the winter time, it's like a kind of dry and drier, like a cold. So the trees go to hibernation. It produces a peak in the CO2 concentration in the Mauna Loa, and in the summertime, the CO2 uptake is strong. Then it becomes a trough in the concentration time series. And so then that we see here is also the variability, the growth rate. So if you take a time derivative of this time series here is shown here, you can get this growth rate we call ppm per year now. and then you can see this, and on the background you see an ENSO cycle. So the ENSO cycle basically dominates what CO2 variability you see in the atmosphere, which means there are natural component and then human component, and then each component has a different time scales. So all these things can be tracked and understood. I mean, we already understand these things by our modeling and experiments and many other things. And the below is a bit the things we do not discuss very often are the isotope signature, because in the fossil fuel, when they are in the soil, actually let's say coal or oil, they are actually same, has a same signature of 13C carbon. So in the atmosphere, basically we have about 99.9% 12C carbon, and 13C is the isotope, stable isotope of carbon, and then that has a signature that in the if you take any plant or trees, they have this signature of 13C. So this is the delta notation. I am not going to tell you much details about it, but if you see 13C, you can find the delta C, how the notations are defined. But it has a negative 13C value, when it's less 13C in this plant, in the plant ecosystem. But atmosphere has a value of, let's say, minus 0.6 in the pre-industrial case, when there are no human influence. And now you see that this is on the right axis is shown that it is going down with time systematically. This is because how much fossil fuel emissions you do in the atmosphere, to the atmosphere, and this drags down towards. So if you replace all the CO2 in the atmosphere by fossil fuel CO2, you will get like minus 28 per mil. And then we have, and this all calculation can be matched how much fossil fuel is emitted. Then you also have another tracer, and this is again 14C, but this is not a stable isotope of carbon. This is a lifetime of about 5,000 years. So then 5,000 years is like a too less small time period, right, for the fossil fuel CO2. There are millions of year old plant in ecosystem, plants, biomass. And that has almost zero 14C, because 14C is like only 5,000 or 6,000 years of lifetime. In millions years, all the 14C basically decayed by radioactive manner in the fossil fuels. So there is basically the zero concentration in the atmosphere by default. But then we human also have ambitions to produce nuclear bomb and test them. And you can see the time series of a nuclear bomb testing with time here in the year. And in around 1960s, 1950s, there are many bomb testing in the earth, and many of them are like a bit of open testing, so that if you do underground or deep ocean testing, that 14C may not come out so much to the atmosphere. But this time a lot of 14C came to the atmosphere because of the nuclear bomb testing, and that actually increased this 14C. But then because now the testings have become changed, the not so many, it is going down again because the fossil fuel CO2 is diluting this system. Because we are not in thousands of years now that this will decay radioactively, but we are actually diluting by the fossil fuel CO2, which is zero 14C, and so it is coming down with time. And then there is also, we know that if you burn something, we consume oxygen and we produce CO2. So then if you're producing CO2, that means you should be like a consuming oxygen. And there is also measurements of oxygen from the different places over the earth. And it started from 1990s by son of the Dev Keeling, Ralph Keeling, and it is actually going down in the atmosphere. You can see that. So all sorts of information we use in our studies, and we have to use, also you have to use it, and how much we make in India, how much we get from outside, doesn't matter actually. We have to use them and develop our understanding of the global carbon cycle. I'm just giving you some examples here, but there are lots of observations available. We are just putting a summary in like a, and then so every slide I also have a figure number. So these figure numbers correspond to the IPCC AR6 figure number of chapter. And so figure 5.6 means 5 belongs to chapter 5, and figure number of chapter 5.6 is a 5.6. So yeah, you can track them. So all sorts of things happening, and then if you put all the summary what I have said so far, you can come up with something called we call airborne fraction. So this is also a very important part to understand, because whatever we emit to the atmosphere, not everything is accumulating there. There's something more happening to it, and this is what is defined here. And something we call airborne fraction means how much of the anthropogenic CO2 actually remained in the atmosphere in the past 60, 70 years or 80 years. And so this is what the plot it shows here. So the anthropogenic emissions, which is like from land use and fossil fuel, changing by the red line here. And then we have the and also background is the ENSO cycle, and then you can calculate depending on how much is emitted from the fossil fuels, land use change, and how much is actually uptaken by the forest, and how much is by the ocean. They all taking up CO2 from the atmosphere and helping us to not increase CO2 in the atmosphere so fast. And there are also volcanic eruptions which also have a signature in this airborne fraction, because if you have a very big volcanic eruptions, they actually produce a blanket of aerosols, sulfate aerosols in the top of that atmosphere, and it reduces the temperature of the earth, and so then the uptake efficiency of the terrestrial ecosystem increases. So you see a negative anomaly in the airborne fraction. And this is why I'm showing this. This is actually becoming extremely important metric for us, how you evaluate, how you track the health of the in Earth ecosystem. And that has been very much used depending on what we have done and how it has changed. So this is our historical knowledge, and we can apply that to the future. And in this future, we are making this future by running Earth system models, which includes all the dimension of the Earth dynamics. So land ecosystem, ocean, the human activities, and then human activities are also like projected into the future, that we call shared economic pathways. This is again produced for IPCC AR6, and they are like a different scenarios. And since the scenario are designed so that we can say, okay, what kind of policy decision is possible and what is not possible, or what happens if you do not follow at all anything. So the blue here is the most preferred ones. The people should have to reduce greenhouse gas emissions very soon, like actually right now you should be reducing emissions, because this is 2015 and this is about 20. And then other ones is again slightly slower rate, and this SSP 1, 2 are the kind of temperature range by if you use this kind of emissions of CO2 to the atmosphere until 2100. And that means that if you do not do anything, and if you like become more, you don't care about the environment and do the economic development as you have been doing in the same path, economic development is not prohibited, but prohibited by the way you want to do economic development. So there are two different things. So you could also probably follow this path or this path, but it's still economic and still grow. And those policy has to be defined, and this is what is done in this case. And if you do that, you can produce this is a time series of historical CO2 emissions, CO2 uptake in the ocean. So ocean is very stable, and then it continues to uptake CO2, but land behaves very differently, because land has a very strong CO2 fertilization effect. And then that if you increase CO2, and also land use change is happening because you clear the forest for our use. This has been already discussed a lot about land use. So then the land use actually dominated until about 1975, because different countries are developing at different stages, including like I mean, we know that how much you deforested for example, even the US was like in these times was developing very fast about 1900. Before that, Europe was developing very fast. Now that in this time, India, other countries where the agricultural revolution happened, they started to clear forest and produce more crop in field, and all the things happened. And then now the CO2 fertilization actually basically taking over, because your CO2 has increased in the atmosphere very fast in the recent times. And then we are actually seeing a reduction in the carbon, a reduction in the negative CO2. I mean, that means our carbon is actually growing in the forest ecosystem. So until this time we are losing carbon, but now we are starting to gain carbon in the ecosystem. And so we need to continue this path to be able to like maintain that kind of airborne fraction. And what is new in this IPCC AR6 is also that we are able to actually use inverse models to calculate or to verify the Earth system models. The one used in the IPCC AR5, which is CMIP 5, and what is being used in AR6 and IPCC in CMIP 6. So what this comparison shows that with latitude, if you plot the carbon uptake for the land and ocean, we can conclude that the Earth system model has improved compared to in CME 5, which is a very good news. And actually, you are moving in the right direction. And we can also do like many details and analysis. So I think no need to discuss here. But all the things, because there is improvement in these things, we get a better agreement in the like a inverse model with the Earth system models. This is a kind of a growing field, and we are also using even the GOSET data or CO2 data to verify Earth system model nowadays. And these things it's a very new field evolving right now. And so, as I said, like this is our present, and this plot basically says you that how much CO2 if you emit, and this is basically coming from the projections I have shown you the SSPs, and you can accumulate, cumulatively accumulate this carbon to the atmosphere by gigatons, and then you can see what fraction of the CO2 are actually remaining in the atmosphere in the gray. It's either in the bar or in the wheels. You see here the gray part is the amount remaining in the atmosphere, which is the airborne fraction, and how much is going into the land and ocean, which is shown by colors, like colors in different wheel or the bars. So what basically it suggests that if you are not following the low emission scenarios, which are in blue, that means you will be moving towards the lower airborne fraction. That means the land and ocean will uptake less fraction of the anthropogenic CO2. And that means your CO2 emission, CO2 concentration in the atmosphere will increase faster because you are removing less. So if you want to improve your health of the ecosystem and everything else, so you need to follow a low emission pathway so that we are able to also remove more amount of CO2 from the atmosphere. So these things are very educative for us, and to make policies like you want to keep your atmosphere healthy, you want to make policies and keep your ecosystem healthy, make your policy to go low emissions. All sorts of things have to be combined together when you discuss about the greenhouse gases mitigation policies. And as you said, like if you do not follow the low emission scenarios or low SSPs, low emission SSPs, we are actually basically threatening the land carbon sink by deforestation, drought, and fires. So this is some sort of example here. What happening? Also, I said before, the CO2 is increasing in the atmosphere, and you can actually increasing the global surface temperature. And there are two effects which is in this cycle. One is the fertilization, because if you increase CO2 in the atmosphere, the plants are happier because they can assimilate, they can get easily carbon from the atmosphere to assimilate in their photosynthesis. And so it increases sink. But then if you bring these disturbances, this is a natural cycle. We like this. Like fertilization happens and increase sinks. Also, you can productivity of the ecosystem or the crop and everything like are discussed also before. But then if you bring the disturbances by the global warming, the fires, drought, and reduce sink capacity, then actually it will feed back positively to this CO2 growth rate. And we also know this. We have examples from this experience is that when you plot from the historical emissions, for example, this is a CO2 flux changes, flux anomaly from year to year. If you take and the uptake means negative, so they're removing from the atmosphere, and release means you're releasing to the atmosphere. And this is if you plot them with the global surface temperature change, which is GSAT, which is the brown line here. You can see that with the El Nino, and the El Nino is shown in the background. So if you have a El Nino conditions, you actually have a weak uptake or a strong release, so that you have a net release to the atmosphere. And this is under the high temperature and the low precipitation conditions in the tropical land mainly. And there are also and this brings to the fire conditions or the drought conditions in the Amazon forest, for example, Indonesia, the tropical areas, Africa, savanna. So all these things are very much strongly affected by the El Nino. And there are also evidence nowadays coming up that because of the global warming, we are talking the more drought is happening. And this drought, if the drought is like recursive, like it happens more frequently, then there is a cycle which goes into the ecosystem, which is called like a forest dieback. So if you keep having a drought more, so that trees goes into like a death, a permanent death in them, so that they don't recover again. So in normal conditions, in the El Nino cycle, basically tree can recover. But if you have a recurrent drought and fires, that there is no chance of the tree to recover. That means your sink efficiency on our system will reduce significantly. And then I also say that ocean acidification this has also a big effect on like you do this very simply in chemistry. Binu, I think, can tell you a lot about this. And then you can actually, because of CO2 going into that ocean, you have this ocean acidification. And what happens in the ocean acidification, that you are actually, the corals might die. Actually, coral death is already reported in many places over the ocean environment. You might see in the places like in our Lakshadweep, Andaman kind of areas too. And then there are less growth in the cells of the sea urchins or the many other sea fish. In Japan, basically, we are like eat a lot of sushis, where they can rice and toppings with the seafood, and that might also, the resource might go down. So I mean, this is not only sushi, but many other seafood resources will go down with time. And so this brings us to again one of the things we talking about, the carbon climate food nexus. So the CO2, this carbon climate food nexus actually feedback actually also linked to the very much into food, and this is also talked about with Atul in much details. So this is kind of a very nice article I saw that it came out recently by some Indian writer, and it came in Nature. And so this is kind of a, let's say, an example of a healthy diet. And what is happening right now is like let's say this is the kind of, if you go by continent to continent and see that the color means that we are overtaking those kind of sector of food, which is like vegetables, animal protein, or fruits, or dairy. So there are different colors. And gray means we are not taking as much as you need. And another very key number here is that how much of the percentage of income goes into food consumption by continent, right? This is a very, very nice diagram. And you can see that North America, they actually eat a lot of meat and dairy. But if you go to like South Asia, where we are mostly living, that we are actually eating more vegetables, but then still not up to the mark which is needed for a healthy diet. So we are actually basically, except for the starchy vegetables, we are actually under the consumption for many things. So now how you will balance your healthy diet and how you reduce the climate change, all has to be like a very much, I mean, very much a more integrated studies are needed to understand these things. And so it also depends on how much the food cost. I don't know how the subsidies or the income ratios. The food cost in the US is very, very cheap. It's only 4% of your income which goes to food, but whereas in South Asia, 65% or more than half of the money we earn goes into the getting food. So it's a very different situation when you talk about the policy of food embedded in the greenhouse gas embedded in the food system. And another things like we were also discussing that per capita income, per capita CO2 emissions versus the total emissions of a country. So India is kind of a third largest emitter of CO2 right now, but then sometimes that is also counter and argued by the say that we actually emitting per capita much less. So here is Southeast Asia, where Southeast Asia and India is explicitly shown here. India is like here. So per capita, which is shown as a bottom axis, and the bars, you can see that India is very, very low compared to any other country, and even compared to global average, we are much lower emitting the per capita but then that is not, I think, the metric of evaluation. I would say that this is something else, which is like a CO2 emitted per kilowatt of energy. So when you produce energy, how much of the CO2 actually emitted from your power plant or the other resources. So in this case, and which is shown as a dot here, like gray dots, so which means that India is actually one of the worst country in terms of energy production. Like your energy productions are not green, not clean. So you are not, although we are burning coal or oil like any other country, but I think our the power plants or the distribution system, something is wrong where we are getting very less benefit out of what we consume in terms of CO2 or the fossil fuels. And so then, of course, there are discussion that many of you might have heard in the COP26 that the solar power should be like a solar grid can be augmented, and you can actually what the whole idea in this case is that we can take this this dot towards this side. So whether you do it by solar power, whether you improve your efficiency of the power plants, whether you efficiency of the distribution system, I think one thing will not work here. You have to bring a whole suite of options to make this happen. So these are kind of the things I think I wanted to tell you here. I think I have about 5 or 10 minutes to speak.
Yeah, so, please carry on.
Yeah, so I'll go to the little bit into the methane, because methane is also another second most greenhouse gas, and it has a lot of chemical feedback into ozone and other species, and we discuss a lot about it in our daily life. So methane is another species studied extensively by us and many other people in the world, and what you see here is that so many of the methane emissions are actually anthropogenic. At least half of it like anthropogenic emissions, and say animal or energy exploitations, the coal mines or oil wells, or rice cultivations. But anyway, so if you put a methane emission map in this way, is that you see that the most of the emissions of methane is happening where actually people live. I think it's more like a proportional to the density of the population. And it's very unlike CO2, which is like has very strong power plant emissions or something. Methane emissions are more distributed because people it linked to our waste management, animals, so everything we are actually dealing in our daily life. So every resources are close to our civilized our cities and all the things. And some emissions obviously are wetlands, which are like natural emissions. They are a bit off place, but you can see that how closely we are linked to the methane emissions, and all the methane emissions which is actually happening in the atmosphere, which is shown as the bars here. So the left bar, these are like 4 decades are separated by the 4 lines. You can see that there are 4 decades, and then within each decade there are 2 bars, right? And one is colored. Obviously, the emissions are colored by natural and anthropogenic sources, and the loss. So all the for CO2 there is no chemical loss in the atmosphere, right? But for methane we have a very huge chemical loss. So it's actually these 2 emissions and loss are kind of, I would say that if you just look at a first glance, it's okay, this is balanced. We don't care about them. But then only this small amount which remains in the atmosphere actually produce this growth rate in methane concentration. And it also so happened that around 2000 to 2009, the emissions and loss are actually quite balanced. And then we see that the growth rates actually flattened for the methane. That's also because it gives a hint that methane is a chemical lifetime of 9 to 10 years. Basically, in our IPCC assessment, which is 9.2 years. That means if you do not emit methane extra, you will actually equilibrate your concentration to a value which is like equivalent to this emissions. So then if you make a policy also for the future, so if you reduce methane emissions, we can actually get benefit in 9 years. Think about that. But also if you remove, if you stop emitting or increasing CO2 emissions, we will not see the benefit very immediately, because the CO2 still grows up in the atmosphere because you are emitting CO2, and then there's no loss for it except for the uptake on the surface. So these are 2 different species and a different perspective we bring in when you think about the policy. And then we can actually discuss these things, and we can again make a growth rate plot of the CO2 methane concentrations. And what our study says is that Naveen did a very good analysis recently, and that we can actually assign using the inventory emissions. So inventory emissions also for us plays a very significant role when you do the top-down inversion estimations, is that we can look at each sector, which sector is actually driving the growth of methane. And our inverse models gives you total emissions for the regional scale and the global scale, and we can link each of the regional scale to each of the sectors and say that, okay, this model is doing well, or this inventories are not doing well, and then we come up with this kind of summary that oil and gas was a more dominating factor for the growth rate, and then now in the recent times it's more mix of the things. You have coal mining, you have livestock farming, everything has actually intensified in the recent times, because the Chinese economic growth, Indian economic growth is driving the global growth, right? So that means all the things are new, they are new economies. So the new economies comes in, they actually consume more and more. much faster in consumption rate compared to the matured economies. That's a basic theory here. And you can see that everything consumption has gone up, and you see a regrowth of methane in the recent decades. And so you can, as I said, like you can also go into every region of the earth, and you can see that how much is the natural fluxes changing. It's the blue line here, and how much is the anthropogenic fluxes changing, which is shown as the black line here. And actually, you can go again to the figure we have in the IPCC and the big cross chapter boxes and read there more details. I will not go here. And again, we can also go into details of the each sector for each country. And these all informations are available from the inventory, and we actually validate by inverse modeling, I would say, and slightly correct them. And then we can also discuss this, what sector is more important and how the sectors can be changed by what kind of policy. So one thing we discuss also, yesterday also discuss a lot that enteric fermentation is a big emission from India. And this is like a sensitivity issue, but I think we have to discuss like how we can manage this. It's not about like stopping it, but how to manage best. And same thing, and enteric fermentation actually increasing very fast in Brazil because there is meat production hub of the world, I would say. And so this is what that we are talking about, the emission intensity of the beef production. And so it's very large, and you can see that is happening in some countries. And another thing we will also notice here is that you can actually reduce emission from a sector. And for example, you can see the rice cultivation in Japan. The area of rice cultivation has not gone down, but the practices, rice cultivation practices, have changed. And recently we discussed about these things, about how can you reduce the emission from rice. For example, there is a cropping system. People talk about intermittent flooding, how you plant your things. And we have actually experimental site in Tamil Nadu, Aduthurai, where we have also shown that if you go to system rice intensification method, SRI or some MSRI, we can actually reduce methane emissions significantly even from Indian rice emissions. And then China has recently acted on the managing the coal mines well. So that you can also see the reductions in at least the stabilization of the coal mine methane emissions are occurring, and we can actually validate, see this from our observations. And I think all these things are happening. So I said I will little bit talk about the additive forcing. I think this is just one slide here. What is coming from the chapter 7, figure number 8, is that again I have shown this in as a bar, but I think you can see how it is changing with time. And in our chapter, what we showed also is that in the recent, so if you go back to like, if you take like a scenario from let's say 1850 to 2019, like a whole period of IPCC assessment, which is shown as a brown bar here on the left for CO2, methane, and N2O and other gases. So you can see here, you can see that methane was actually 20% of the actually, if you say in CO2 80%, methane was 20%. So almost 1/3 of the CO2 methane was contributing to the radiative forcing. But if you take the very recent times, which is in the last 20 years, so contribution of methane has gone down, which is a kind of a good sign for us. But again, and because I said that the 2019, so one of the decade, actually methane did not grow at all, right? So this brings this contribution down. But if the regrowth happens from 2007 or 8 again, if you take next 20 years, this will again go up if you do not control this. So these things are all, these dynamics are all happening right now, and you can see them, their contribution changes with time. And then, yeah, you can also do this kind of assessment for every region of the globe, and every by emission weighting, by the global warming potential, this, that. So all things are being argued now, what to be done, and then how much is remaining for us to consume. I think all these things I will skip now because we keep some time for discussions. And I think these are my take-home messages. I will just stop here. Thank you.
Thank you, Dr. Praveen. It's a very wonderful talk. There is a lot of questions are there. I will read them one by one. The question is, I think, from Pramod about the atmospheric oxygen concentration, how its oxygen concentration can be measured.
Oh, you mean the technique of the measurements?
Yeah, maybe like how and is there any reference paper on this? How
yes, so that you just search maybe the Ralph Keeling. So this, just go to Scripps Institute of Oceanography. So they have obviously much details. This is, I think, based on some sort of a, I don't know what instrument is that. So the one thing then in that one I can just only say that these measurements are extremely difficult for oxygen, because the problem is that we have a 21% of air mass, which is oxygen, right? And we are detecting, and then CO2, for example, is a 0.04%, right? So then that means that you are actually measuring these changes in 0.04%, which is very easy. But if you measure that it's a similar amount of change, which is kind of for oxygen in 21% of the air, it is extremely difficult. So precision was the main problem for oxygen measurement. Oxygen measurements per se is very simple. The precision of this instrument was, so there is a story that I think that Ralph Keeling, he was doing PhD in Harvard to develop this instrument, and he took almost 10 years to finish his PhD, because he was not getting PhD without making this instrument. So this is that difficult in Harvard University, the best lab in the for making measurements or in instrumentation. So I think better to read that paper and his papers, Ralph Keeling.
Okay, next question from Mihir is that how we can distinguish the carbon from atmosphere, atmospheric carbon from oxysphere, or like that. We have distinguish the. In fact, I think natural and anthropogenic. How we can distinguish the carbon.
Yeah, so I think this is about, again, in the same slide. I mean, I try to explain you here. So we actually use the isotopes, stable isotopes and the radioactive isotope of carbon to distinguish between the fossil fuel and the anthropogenic and other sources, and the natural system, which is the El Nino, for example, here. So yeah, again, I will refer you to this chapter, or read some fundamental papers on this. I think we can give you many references.
Yeah. Next one is from Chaitanya. The SSP 1.9 is the extreme reduction. Is it feasible in reality, or what could be a more realistic route?
So these are all actually depends on the, I think, the wish of the people. And I would also say that this is very difficult to achieve, given the dynamics right now among the countries. I think there are a big, I would say that it's not like nobody is compromising on their lifestyle yet. So until that happens, this is impossible. I mean, you might have followed some of the discussion in COP26, is that people come up. Also, like, in our report, we put this figure. I just trying to show you that. This figure we put here, just to show that how important is CO2. But in this COP26, we are a bit depressed or disappointed, is that CO2 was not discussed as much as methane was discussed. So methane has actually become less important, at least for the current scenario. But CO2, there is no escape from CO2 reductions. And people did not compromise on their lifestyle, except that we are hoping for the future, that we have a solar grid, we have all the things. So nobody talked about presently what we can do. So it's mostly people are promising in the future, but then people have done less on what you can do right now. So I would agree with you that, but then we have to still be optimistic and hopeful that next COP in 27, something will come out.
Yes. So next one is from Vaishnavi. That is, what is the effect of volcanic eruption on radiative forcing?
Yes.
Maybe you can. What is the effect of volcanic?
Yes. So here actually we are in the right slide here. In the right panel, you see here, the volcanic is the green one. I don't know that you can see the color. The volcanic, it is a green one, which is going with the black here in the part, and then it's again green here. And so this is what the volcanic contribution to the global Earth surface temperature change. And when there is, as you know, that when there is a volcanic eruption, there's a lot of sulfur dioxide goes into the atmosphere, and then they becomes like sulfate, which is a kind of aerosol. It's a particulate matter. It can scatter the sunlight, the visible light. So the visible light cannot reach to the Earth's surface. That means the heat is actually cannot come into the Earth's surface, and that actually gives us a cooling on the surface. That's why it's a negative effect on the atmospheric heating. So you have on the negative side compared to the greenhouse gases, which are on the right side, positive side.
Next one is from this Miguel. That's a very fundamental textbook question, so I may skip that about the CO2 warming effect on troposphere and stratosphere. So I'll go to Pramit's question is, what is the effect of CO2 fertilization on induced enhanced photosynthetic carbon uptake on the nutrient cycle, such as nitrogen, phosphorus, etc. Is this uptake limited by nitrogen or phosphorus availability, or does it contain a natural nitrogen or phosphorus cycle?
No, I think that of course they are all nutrients, and you know that for anything to form, you need nutrients and micronutrients. But at the moment, we don't see see a problem with the nutrient limitations right now. But when you have a further CO2 fertilization increase, it might see a limitation. I think that's what I would say at the moment. And actually, the previous question was very important, like global warming for CO2. I think on the troposphere and stratosphere, that's kind of a nice question. This is what the whole idea of CO2 heating and cooling thing came. As Krishna was saying, the Manabe-san's papers in 1960s. That's quite fundamental though, but I think it has a very interesting picture because CO2 is a black body. It actually absorbs infrared radiation at the surface, but if you go to a stratosphere, actually it release the heat because there's no infrared radiation there. So it's a negative effect in the stratosphere and positive effect of the heating in the troposphere. You should read that. This is very interesting papers.
So again, continuing about that food consumption, he has a question was that about the food consumption pattern. So what the main question is that.
What is the question?
It's a lengthy question, which part are linked to the consumption part? Greenhouse emission or India and the US, they are comparing.
This one, I think this one.
Yeah, that one.
Yeah, I mean, this is like I would say that this pattern, what you see, of course, it is the economics, obviously, what we eat, because you know that the meat is so expensive in India. Even if you can produce a lot, but if it is still so expensive compared to our other country, like you can say, let's say you can buy vegetable 1 kilogram is much cheaper price, or even the rice or the other potatoes and everything compared to meat, or maybe 10% price, I guess, compared to meat. But if you go to the other country, like even Japan, where I live, where the meat and vegetables are the same cost by weight. If you go by weight per gram, it is almost same cost. But if you go to US, it's like an opposite. Like vegetables cost much more than meat. Meat is the cheapest options for the people to eat. So the consumption generally goes up for the meat and dairy in the US. It's also because of the cost, the finance of the food market. And so then naturally fruits and other things, the whole healthy options are more expensive actually than plant protein or fruits. I think they are more expensive than this one. So one of
Prabhita, actually,
yes.
Yeah, my question was actually in this sense that you are saying that a larger fraction of total income goes into the food, into buying the food in India compared to US.
Yes.
So I was just curious, although it may not be very pertinent to your talk, but it is relevant. I was curious to know then why there has been, strong opposition to India and such countries providing subsidy to the agricultural products, which can further bring the cost of food product down and make it more available to the Indian consumers. My question was in that direction, and it is directly linked with the consumption pattern and GHG-3, as you said. So that was my question.
Yeah, I mean, I think this will be very complex economics, I think, because the salary also is very different in the American system, right, compared to Indian system. So the average income, per capita income is also important in this 65% number. So average American spend much more on the absolute sense on the money compared to average Indian or South Asian, but the fraction of your salary which goes into this. So many people are age, like in our country, even I have seen people like who just earn to live, nothing else. So it all goes to this number.
So that is the question. So if the countries like India and all, which has less income per se, to subsidy to the agricultural products, then the price of food comes down. And
no,
people,
but then it's an international market, right? You cannot survive in this system because you have to buy. How can you buy so much things that how much subsidy can be given? I think anyway, this is like a different topic. I think I am not expert on that for sure.
okay.
Next one is from Binu. The gram carbon dioxide per kilowatt energy in India appears to be very large. Is this due to extensive coal usage in India for energy production?
I think it is mainly should happen because of the inefficient power production system. The power production system in India, I suppose, is less efficient and less well managed. And then the another thing I also feel that the distribution system in India should be like a poor. I have not seen like a why it is so high, but it is high as many other country. So it's not surprising. But then India being a densely populated country, I think this can come down if you have a more improved system of the production and distribution.
So next one from Gayatri, whether we can control the natural sources such as wetlands, or what measures we can do for the controlling this wetland methane emission from India.
Yeah, I think wetlands. I think in India is not so much, but I think as I was mentioning that rice fields are quite large in India, and we still do a lot of flooding in the rice irrigation. So here you can see that I don't. So what I am showing in these plots is that the top 1, 2, 3, 4, 5, 6 emitters. So for any given country, the top emissions 6 sectors of emissions. So here you don't see wetlands for India. And so, but you see the rice cultivation here, right? Cultivation can be, as I say, you can improve actually by going to system rice intensification methods, where you don't flood the rice field continuously. And this is one of the things we can easily implement, and it actually helps farmer because they are putting less water to the field, and then you can efficiently provide fertilizers to the trees or plants when they need. And all sorts of management can be done on this actually to help farmers and also help in climate environment.
Prabir, can I have one question on this slide?
Yes.
How do you? What is the error estimate in terms of percentage in this estimates you made?
This is from the Edgar actually. This is from Edgar.
Error. Can you calculate the error? This.
But error should be. I would say that it's a for our if I put in our model and then I simulate the concentrations, I don't see that we did not need a much change for these countries, except for China we needed some decrease in the emissions. These emissions are too large, but I think any other country would not need to change emissions, which means that the total emissions are quite good, quite okay, and that within I would say that 10-20%.
Okay.
Yeah, for country totals, but each sector may be quite different. But I would say that not so different. Again, 20% would be the error bar, I would say.
Japan, they have reduced the rice cultivation. That how it is reduce the rice consumption, or what is the measure?
That basically system like in intensification, they do all the managed rice production. No more irrigation, no more flooding irrigation. And of course, sorry, I mean you should also notice that the y-axis is not same, right?
Oh,
so the reduction is not like so it's like let's say from 3 teragrams to 1 teragram.
Understood.
So 30% reduction, right? 30% reduction. But for example, India, we actually have more than 6 teragrams of methane emissions just from rice. So so the whole the rice emission from India itself is much bigger than the whole Japan emissions.
Correct.
So the scales are very different. I think the opportunities are big, I think, here.
So Pravir, while you are in this topic of rice for Indian and suggesting about drip irrigation as an alternative to reduce the methane emission, it may not be feasible for entire country, but it may be feasible for what you have selected close to maybe Tamil Nadu.
Yes.
Because in certain part of the country, you cannot avoid floodings because anywhere during the time of southwest monsoon, farmers get excess rainfall and that they cannot remove it from the field despite their, say, strategy to reduce it by drip irrigation. So is there some way one can use some other engineering technique to reduce the methane emission, even flooding situation?
I think and this is not new, right? I mean, I think I remember the Manmohan Singh's government time, they're talking about linking the rivers. There are some idea about linking rivers, which means that is basically water management, right?
Yeah, so yeah, but that has their pros and cons, even linking rivers. Yeah, so now is there something other than using drip irrigation, something like gels or others can reduce the emission scenario for Indian case?
There are something like if you use more ions, some ionic fertilizers, you can actually reduce methane emission because you can oxidize methane in the soil. But I think they are expensive options, and then it's not like so farmers has to pay for it, or the government has to pay for it. But I think that linking rivers is not pros and cons, but it's also like that you have so many floods, right? You have floods and you have droughts. That has to be managed for any country. I mean, you have to think about that. I mean, droughts are like it's both bad for human beings.
Yeah, so regarding your coal thing, see, Indian coal is not clean coal. First of all, it's a dense coal, and we are having most anthracite as one of the coal which is more dense in terms of carbon content. So because of that, the emission efficiency goes high. So now even for steel industry, we use some of this coal, and many of the steel industry, they purchase coal from Australia because that has high potential. So now it's a difficult challenge, but maybe clean coal, maybe something which might come, or maybe methane from coal bed, maybe other alternative to reduce the emission which is coming from thermal powers.
Yeah, I mean, all sorts of things. I mean, yeah, I think that people basically know how to do it, but I think you need a planning and wishes.
So 3 more questions are there. We can ask quickly answer. One is from Ravi about that he is saying the radiative forcing from CH4 is decreasing. Is it true for our regional perspective also?
No. Regional perspective will be different. This is a global perspective because regionally the dynamics is not same.
Okay.
You see this one, like regionally, not every emission of methane is going down. So if this methane emission is going up, that means you are actually not reducing the fraction.
Next one is from he is asking that the CO2 removal that there are different processes, methods to remove CO2 from the atmosphere. Whether these processes are beneficiary for future?
Yeah. So we need all the options because we cannot just do by naturally all reductions of CO2 which we need now. So we need to bring technology. We need to bring all options.
And from Imran, it is whether the ocean acidification changes its specific heat capacity, whether it will change.
I think heat capacity will not change by ocean acidification. I think ocean acidification basically have an effect on the life of the sea, even the ecosystem of the sea. It doesn't have nothing to do with the heat capacity of the. But then heat obviously goes into the ocean because you are warming the air temperature.
Yeah, I think one next is that whether the electric vehicle can be reduced emission. Of course, I think he is believed. And then I think one more question is that whether CH4 emission comparison is whether it is area specific or something like that. Pramit asked. Can we see area specific CH4 emission comparison among the countries?
I mean, methane emission per unit area among the different countries.
Yeah, unit area has no meaning, right? So we want to global, again, we are talking about the global emissions. Yeah, here you can there unit area, right? This is unit area emissions.
Maybe you can discuss later. So our time is running up. So thank you, Dr. It's a very nice talk.
Thank you very much.
Can we go to next talk or some break is secured?
I think we can take a 5-minute break because we already crossed 11:07 now. And in that break time, maybe the next presenter can load the PPT and we can regroup at 11:15. 11:11. Okay. 11:11. Thank you.
Okay. So meantime, Dr. Sajeev can test his rights, all things. He is available. Dr. Sajeev Philip, are you online?
He is online. We will bring him up as a presenter. Please hold on. I'm sorry. I think we did not notice that he's in the participant list.
Okay.
Yeah, you can put up your slide, Dr. Sajeev.
Hi, Dr. Siddhi, are you able to hear me?
Yeah, you're loud and clear. So can you show your slides? Then we can test.
Yeah, just a moment.
Fine, full screen, please.
So, are you able to see my screen? The slide?
Slides, full screen, please.
Yeah.
Yeah, fine. Fine.
Right.
We will wait for another 2 minutes.
Okay.
Avinu, shall we start?
Yeah, I think we can start 11 now. Yeah.
So I'll give the next talk is by Dr. Sajeev Philip. I'll give just a brief introduction about Dr. Sajeev Philip recently joined IIT Delhi after his a long career in Canada and USA. So his main area of research is the disturbance is coming from yes to mute or technical issue.
I think some background noise there. Can you speak up?
Okay. So he has a interesting that estimating the greenhouse fluxes, and he has a lot of works on the geoscum modeling and I think we have to welcome him because our Indian greenhouse community. So the onwards he will be a strong member. I hope so. So Dr. Sajeev, you please carry on your talk.
Okay. Thank you, Dr. Siddhi. First of all, let me thank you all for providing me an opportunity to present some of my research here. Yeah, once again, let me introduce myself. I am Sajeev Lib, recently joined as an assistant professor at Center for Atmospheric Sciences at IIT Delhi. Today, my talk will be about some of our studies focusing on estimating some of the natural carbon fluxes using NASA's Orbiting Carbon Observatory to satellite, or CO2 satellite. Today we will be focusing mostly on South Asia region, comprised of India and 5 neighboring countries. This study was conducted during my time at NASA Ames Research Center. I would like to thank my colleagues who contributed to this work, modeling and evaluation support from Matthew Johnson from NASA Ames, David Baker from NOAA, Saurish Basu and Benjamin Porter from NASA GSFC, and observational contributions from Yogesh Tiwari from IIT Pune, and K. Indira from CSIR, and Michael Ramonet from LSE. This talk is organized into three sections. First, I will give a very brief introduction to NASA's CO2 satellite and describe how it can be used to explore research questions, science questions related to the global carbon cycle. Our focus here will be mostly on terrestrial biospheric CO2 fluxes. In the second part of the talk, I will be discussing mostly about a multi-model intercomparison study initiated by the CO2 science team. Third, and a major portion of this talk will be about constraints imposed by CO2 data on these regional terrestrial biospheric fluxes of horizon South Asia region. This work was submitted as a research article in JGR. It's in review now. I'm expecting its publication within the next 2-3 weeks. I would like to thank all the contributors, funding support from NASA, Academic Mission Services, Computing Resources from NAS division at NASA Ames, OCO2 Science Team, Geoscom model developers, NOAA ESRL, Contrail data providers, and a number of data providers and collaborators. As we all know, a better understanding of the global carbon cycle is a requirement for predicting future climate. Figure on the right shows atmospheric CO2 monthly mean mixing ratio measurements from the Mauna Loa Observatory for the last 60+ years. Atmospheric CO2 mixing ratios reached 410 parts per million ppm, 410 ppm in 2021. This increase in atmospheric CO2 mixing ratios is mainly due to the human-induced emissions of carbon dioxide. And this steady increase in atmospheric CO2 is directly linked to global warming. Therefore, assessments of future climate requires a better quantification of carbon dioxide emissions and surface fluxes. This atmospheric carbon dioxide is partitioned into 3 major reservoirs: 1, fossil fuel; 2, oceans; and 3, terrestrial biosphere. On the right hand side is a figure from Global Carbon Study 2020, where emissions are from fossil fuels in a gray color, land use change from brown, and these emissions are partitioned into atmosphere, land and ocean, atmosphere in blue, ocean in turquoise color, and land in green color. Units in gigaton carbon per year or petagram carbon per year, that means 10⁻⁵ grams of carbon per year. This land CO2 sink in green color for the last 10 years, showing around 3 petagram carbon per year changes. You can also see important intra-annual variations of around 2 petagram carbon per year. So this terrestrial biosphere plays a significant role in the global carbon budget. This land sink in green color is estimated from an ensemble of 17 models. We call it bottom-up terrestrial biosphere models. Here we have a panel with several maps showing terrestrial biospheric CO2 fluxes from the state of the science global terrestrial biosphere models. Here, terrestrial biospheric CO2 fluxes are represented as net ecosystem exchange, NED, where net ecosystem exchange is the net carbon exchange from the biosphere into the atmosphere. A positive NED means CO2 is released from the ecosystem into the atmosphere, and a negative NED means uptake by the biosphere. Each row shows NED fluxes for different seasons, with the first column northern hemispheric winter and third column northern hemispheric summer. Each column represents global TBMs, and on the left is NASA CASA model. NASA CASA was developed at NASA Ames Research Center, and second CASA GFET from GSFC, SIP4 from Colorado State University, and LPJ from GSFC. In general, we can see that all these models predict similar spatiotemporal patterns. However, if we focus on a regional scale, we can see noticeable differences among these models in the quantification of these terrestrial biospheric fluxes. So the exchange of carbon between the terrestrial biosphere and atmosphere is a large source of uncertainty in the overall carbon budget. So our goal here is to better estimate these terrestrial biosphere atmosphere exchange using models and observational data. As we all know, a major limitation for estimating these CO2 surface fluxes has historically been the scarcity of in situ measurements available. Here we have a figure showing observational network from NOAA ESRL. We can clearly see that continuous measurements are absent in many regions, especially in the tropics and the southern hemisphere. Due to the paucity of these in situ observations, large uncertainty exists in the top-down CO2 surface flux estimates. Satellites comes with a more continuous and dense observations, which increases the spatiotemporal coverage offered by these observational networks. Orbiting Carbon Observatory 2, or OCO2, is the first NASA satellite dedicated specifically to infer these surface CO2 fluxes. From OCO2, we can retrieve XCO2, that is column CO2, and global chemical transport models are used to assimilate this OCO2 data to estimate surface CO2 fluxes. Figures on the right shows the improved data coverage by OCO2 land-aided observations in comparison to in situ data. Here we have a general schematic of our estimation of surface flux, CO2 surface fluxes, assimilating OCO2 and global in situ data. In short, our method is to use spatiotemporal gradients in atmospheric CO2 mixing ratios to estimate top-down CO2 surface fluxes. An atmospheric chemical data assimilation system consists of a transport model and an inversion framework. Here we use the GeoSCM global chemical transport model. GeoSCM is driven with meteorological data from the NASA GMAO. Due to sparse observations, we use a Bayesian prior in the inversion system. We use bottom-up prior fluxes from several carbon cycle models as an input to the inversion system. And we then assimilate CO2 atmospheric mixing ratio measurements from in situ networks, aircrafts, and we also assimilate satellite XCO2 data, or CO2 XCO2 data. And the inversion framework, we use the 4D-var inversion framework, and the inversion system produces top-down or optimized or the posterior CO2 surface fluxes. Here, we optimize terrestrial biospheric CO2 fluxes and fluxes from the oceans, and we keep fossil fuels and biomass buildings unchanged in the inversion system. Even though we are estimating terrestrial biospheric fluxes and oceanic fluxes, in this talk, we focus mostly on the terrestrial biospheric component. There are inherent uncertainties associated with the estimation of these surface fluxes use assimilating OCO2 and in situ observations. In order to assess the impact of each error sources to these flux inversion models, OCO2 science team is now conducting a formal multi-model intercomparison project, we call it MIP. Using version 9 of the OCO2 MIP, OCO2 data, we call it OCO2 V9 MIP. Version 10, with version 10, OCO2 V10 MIP, which is ongoing. OCO2 MIP is a collaborative effort to conduct global CO2 flux inversion simulations using 10 different global models. There are two goals associated with this project. One is to assess the impact of assimilating OCO2 versus in situ observations in these flux inversion products. And second goal is to develop an ensemble mean level for CO2 surface product on a global and a regional scale. Table on the right shows that number of MIP research groups are participating in the MIP with different transport models, meteorology, and inversion models. All these OCO2 MIP modelers estimate terrestrial biospheric and oceanic fluxes assimilating OCO2 and in situ observations. There are a number of in situ observational data assimilated in the system, and there are some observations withheld for independent data evaluation. Here is a plot comparing OCO2 MIP model output, atmospheric mixing ratio against observational data from Mauna Loa. These observations are not assimilated in the system. So we have a number of observational data withheld for evaluation throughout the globe. And evaluating these model simulations is an essential part of the MIP. All these evaluations and comparison plots are available at OCO2 V9 MIP, V10 MIP website hosted by NOAA. Here is a comparison of prior in situ and OCO2 constrained XCO2 against XCO2 retrievals from the Tikon station at Park Falls. We have more than 20 Tikon stations around the world to conduct a detailed evaluation. So evaluating model simulations is an essential part of these MIPs. Now we discuss our model specifications. Our model, we call it NASA Ames, we do not cast Ames. NASA Ames Global CO2 model. We generally follow the protocols of the CO2 V9 MIP. Our influx inversion follows our paper in 2019 in ECP. For this work, here we assimilate OCO2 land near and land glint retrievals and global in situ observations. In situ is known as IS. We optimize monthly CO2 fluxes, surface fluxes, from 2015 to 2018 at a spatial resolution of 4 degree into 5 degree latitude and longitude using the inversion technique for DEVA with the transport model Geoscom. And for the priors, we use unoptimized prior estimates from the carbon tracker. In situ and XCO2 observational errors includes measurement and model error. We take the quadrature sum of the observation errors. The spread of 5 state-of-the-science global terrestrial biospheric models are taken as any prior error. We estimate terrestrial biospheric oceanic fluxes at a resolution of 4 into 5 latitude and longitude, and we then aggregate them into different regions and on a global scale. Here we show the annual and multi-year mean land CO2 flux from the prior in situ and OCO2. Here we represent a net biome exchange defined as NE and unoptimized biomass burning emissions. So top panel shows NBE, net biome exchange, from the prior in situ and OCO2 for different years, 2015 to 2018, and green bar represent the mean. And bottom panel shows annual NBE anomaly for prior in situ and OCO2 from this for different years. We can clearly see that both OCO2 and in situ produced a global land sink for 2015 to 2016. Annual NBE anomaly values varied between the years, with positive anomaly for 2015 and 2016 and a negative anomaly values for 17 and 18 for both in situ and for OCO2. These high NB anomaly values for 15 and 16 could be the impact of recent El Nino, which led to a reduced CO2 uptake by the tropical terrestrial biosphere. Here we show the seasonality of NBE over the global land. Top panel shows NBE from prior in black, in situ in blue, OCO2 in red. Biomass burning emissions is designated as a dotted line. And bottom panel from 2015 to 2018. And bottom panel shows multi-year mean monthly CO2 fluxes. Multi-year means 2015 to 2018. So prior, in situ and OCO2 constrained global fluxes show similar seasonal cycles with a CO2 land sink between May and August and a moderate source in the remaining months. We can clearly see that the peak of the drawdown in posterior estimates from in situ and OCO2 constrained estimates is larger than the prior estimate. Here we show the comparison statistics comparing these prior and posterior CO2 against global observations, which includes TCON XCO2, in situ observational data OBSPAC withheld 3% of the OBSPAC data withheld for evaluation, and assimilated OBSPAC data and OCO2 lanyard and lanyard which are assimilated in the system. Here we are showing mean bias, standard deviation, RMSE and R for prior in white, in situ in blue, and OCO2 in red. In general, posterior CO2 and XCO2 values obtained by assimilating in situ and OCO2 show substantial reductions in normalized mean bias and standard deviation, and increase in the R correlation. We can clearly see that here. So the overall model performance of our model, AIMS model, against all these observations is comparable to other global models participated in the OCO2 line group. Okay, now we focus on new insights gained while assimilating OCO2 data. That is about the constraints imposed on regional CO2 fluxes imposed by OCO2 data. And our focus here is on South Asia region. You can see the definition of South Asia in this green colored boxes, which includes India and 5 neighboring countries. Now a bit motivation. A better understanding of the South Asian terrestrial biospheric CO2 fluxes is critical for assessing the global carbon cycle. The spatial temporal variability of net ecosystem exchange fluxes from both top-down and bottom models are having large uncertainty over this region. On the right-hand side is a figure taken from Patra et al. 2013 recipe paper. Top panel shows terrestrial biospheric CO2 fluxes seasonality over South Asia region from top-down CO2 flux inverse models. And bottom panel shows flux seasonality as predicted by bottom-up terrestrial biosphere models. You can see substantial spread in the top-down and bottom-up CO2 flux estimates. This spread in the top-down CO2 flux estimates is mainly due to the scarcity of in situ observational data. So here in this study, we are exploring what OCO2 satellite column CO2 retrievals can inform about South Asian CO2 fluxes. Here we show annual and multi-year mean net biome exchange over South Asia region from the prior CASA model in situ and OCO2 with different colors showing different years with multi-year mean value in green. And bottom panel shows annual NB anomaly values for different years. In general, if we focus on top panel, green, you can see multi-year mean in B values. We found that with this study, South Asian terrestrial biosphere is near neutral with annual mean in B of around 0.04 petagram carbon per year, estimated by assimilating in situ or OCO2. We can clearly see contrasting posterior annual NB anomaly values imposed by in situ versus OCO2 observations. We can see a positive annual NB anomaly for 2015, negative for annual for 2016 with in situ, whereas OCO2 data differs from this, which shows a negative annual NB anomaly for 2015 and a positive value for 2016, illustrating the differences in flux estimates due to varying observational coverage of these two data sources. Here we show the comparison of this annual mean, multi-year mean CO2 flux in the study with a number of recent previous studies, which includes bottom-up studies and top-down estimates. Bottom-up includes studies aggregated over India from Nayak, Gehlot et al. From 2020 from our IIT Delhi itself, and several other papers. And top-down estimates includes a recent inversion estimate from CSIR, Swati et al. 2011, and recent studies including the Nature paper from Thompson et al. 2016. We also show here estimates multi-year mean, but here the multi-year mean is for 2015 to 2018 from the OCO2 mean and MIP by assimilating in situ and OCO2. And we here in red, we are showing our estimates. In general, past studies have predicted an annual mean flux ranging from minus 0.37 to minus 0.05 petagram carbon per year. Our estimates in the study is slightly higher than this estimate, around 0.04 petagram carbon per year. However, if we consider standard deviation, somewhat consistent with all these estimates. The most robust result found by assimilating OCO2 observations was the constraints imposed on the seasonal cycle of CO2 fluxes over South Asia region. Top panel shows monthly CO2 fluxes over South Asia region from 2015 to 2018. From the prior in black, in situ in blue, OCO2 in red. Biomass burning emissions are not a significant source compared to this NE. Bottom panel shows multi-year mean monthly fluxes, that the mean of 2015 to 2018. There are two features obtained by assimilating OCO2 observations. One is the larger seasonal amplitude imposed by OCO2 data, and the second one is the shift in seasonality imposed by OCO2. OCO2 data in red color produced a larger seasonal amplitude of around 4 petagram carbon per year, compared to the prior CASA model with 1.5 petagram carbon per year. The seasonal amplitude imposed by in situ is also much larger, around 2, which is in a blue color, it's around 2 petagram carbon per year. OCO2 data in red color also imposed a phase shift in seasonality with a larger CO2 source, a peak in April, and a sink in September. Here we show the same figure, that is multi-year mean monthly CO2 flux over South Asia region. In addition to the prior CASA model in black, in situ constrained flux in blue, and OCO2 constrained flux in red. Here we also show fluxes from the MST MIP ensemble mean product for a different for a multi-year mean from different year. MST MIP mean is an ensemble mean of 15 terrestrial biosphere models. So we can assume that our current understanding of CO2 fluxes in this region is well represented by the MST MIP ensemble mean product. Here we also show fluxes from the LPGA model. It's a fully prognostic, meteorologically driven biosphere model, whereas CASA is a diagnostic model, which is in blue. In magenta, you can see the MST MIP ensemble mean product. You can clearly see that OCO2 optimized fluxes, which is in red color is much larger. So the seasonal amplitude imposed by OCO2 is much larger than our current understanding, that is represented by the MST in magenta color. We can also see that MST ensemble mean has a peak source spread out between March and June and draw down between August and September. Similarly for LPJ model. However, for OCO2, we can see pronounced peak source in April and pronounced peak sink in September. Here we show the comparison of OCO2 retrieved XCO2 from Lanyard and Langley modes against model simulated values using prior in situ and OCO2, in situ constraint and OCO2 constraint and the prior CASA model. This OCO2 retrieved values over South Asia is in gray color and prior in black, and in situ constraint XCO2, which is in blue, OCO2 constraint in red. We can clearly see that the seasonal cycle of OCO2 retrieved XCO2, which is in gray color, is larger than the simulated XCO2 using the prior model, which is in black. And we can also see that the posterior XCO2, estimated by assimilating OCO2 in red, better reproduces OCO2 retrieved XCO2 if you compare gray versus red. If you see the comparison statistics, you can see that, of course, OCO2 data was assimilated in the system, and of course, we will have a good comparison of OCO2 with assimilated Lanyard observations. The important point to note here is that a larger seasonal cycle of OCO2 retrieved values over OCO2 retrieved XCO2 over the South Asia region. Now we focus on our comparison with flask observations in and around South Asia region. We have 4 flask observations, one from Hanley, SNG, Singhagat, Pondicherry, and a marine site which is outside of the PPL. We can see measured values in gray, prior in black, in situ in blue, and OCO2 in red. Generally, model values are having high bias. This large bias in the model could be due to the representativeness issues arising from the proximity of local sources to and local emissions and regional biospheric sources to these monitoring stations, and of course the coarse resolution of the geoscum model, around 400 and 500 kilometers resolution, which is not capturing the land ocean dynamics and complex topography from these stations. We also found that most previous studies found poor performance of their models in comparison with flask observations from these 4 monitoring stations. We also found that these previous studies, their seasonal amplitude was underestimated by around 30 to 50% in comparison to this data. In spite of this large bias, we found that assimilation of OCO2 data leads to some improvement in the temporal correlation compared to the prior or in situ. For example, we can see that prior correlation coefficient is about 0.37 for the Hanley, and it's increased to 0.68. There was some decrease in the standard deviation also. Except for the Pondicherry, you can see that the temporal correlation increases with the OCO2, which is in red. So the point here is that OCO2 is better capturing the temporal variability of flask observations. Of course, we have a large bias in the comparison with the Singhagat observations. Here is a bottom panel. We have a plot taken from Chakrabarti et al. 2020 review book, and it's adapted from Tiwari 2014 paper. Here we are comparing Singhagat observations with Mauna Lava, which is in the similar latitudinal range, You can see that Mauna Loa Observatory, we have around 6 ppm seasonal variability, but however, our SMB side, we have more than 30 ppm seasonal amplitude, which most previous studies and our model failed to represent. In this study, we are not assimilating any in situ observations over South Asia region in the assimilation system. So due to the severe lack of these continuous in situ observations for this 2015 to 2018 period, we must use any data available for evaluating the performance of the model. We acknowledge that there are other short-time studies. We have a data set from Contrail in the OBSPAC data set. In that OBSPAC data set, we have 2015 and 2016 observation near to South Asia region. In 2015, we have some observations over Sri Lanka. So we make use of these observations near the South Asia regions to make an evaluation. Here, Contrail observed monthly mean values are compared against model simulated mixing ratio, atmospheric mixing ratio values from the prior in black, in situ in blue, and OC2 in red. These Contrail observations are averaged over the grid boxes shown in the insert. Here, these grid boxes are selected from latitude bands covering the South Asia region and longitudes from 60 to 113. And Contrail data were averaged over the altitude range of 5 to 13 kilometers. We can clearly see that Contrail observations in gray show a peak around May and a sink around September. And we can also see that the seasonal pattern of Contrail observations was better reproduced by this posterior CO2 constrained with both in situ in blue and OCO2 in red. Much better than the prior, which is in black. So important point here is that posterior CO2 is better capturing the seasonality of Contrail observations. Here we compare our prior and posterior fluxes with satellite-based NE proxies that are NDVI, EVI, SIF from several satellite instruments. On the left, we have a figure comparing these CO2 flux monthly mean fluxes from 2015-2018 against NDVI, EVI, and SIF data from number of satellites. As expected, we get a clear negative correlation of these fluxes against these vegetation indices. On the right, as in a table, we can see that the correlation coefficient of NDVI, EVA, and SIF against our model simulated values in white, prior CASA model correlations, in situ in blue, OCO2 in red, and we here also show the comparison against LPJ prognostic model. We can clearly see that OCO2 correlation of OCO2 is much higher than the prior or in situ. So important point here is that OCO2 constrained CO2 flux better correlated with these satellite-based NE proxies compared to the prior or in situ constrained model values. So far we discussed about NASA Ames model. Here we also say that OCO2 constraints seasonality from the NASA Ames model is generally consistent with majority of the OCO2 V9 MIP models. Here we have plots for prior models used in the inversion, 10 inverse models. On the top left, prior models. On the right, we have on the top right we have in situ assimilated fluxes over South Asia region. And in the bottom left, we have CO2 flux over South Asia region constrained with OCO2 lanyard and lanyard observations. Here in red, we have our Ames model denoted and denoted as red aims, and ensemble mean is in black color, and all other models are represented in different colors. You can clearly see substantial spread in the prior models, and you can see the spread reduced with the in situ data assimilation and OCO2 assimilations. You can see in the in situ, we can still have some spread, but if you see in the OCO2 data, most models represent similar temporal patterns. You can clearly see that 6 out of these ensemble members have larger seasonality than the assumed priors. And second point, 7 out of the 9 models have similar phase shift in seasonality as our Ames model. So the point here is that OCO2 constrained seasonality in the study is generally consistent with majority of the OCO2 B9 models when assimilating OCO2 observations. Okay.
Can you wind up in 5 minutes or we get some to discuss?
Yeah, in 5 minutes I will start. Okay. So we also conducted a number of sensitivity simulations to test the robustness of our results, seasonality. Here, South Asian monthly CO2 fluxes and its sensitivity simulations by changing the global prior NE error using a different prior biosphere model, which is LPJ, with a different seasonality than the CASA model, and with a very different, by perturbing, or that is by inflating or deflating CASA NE error over the tropics. And from these sensitivity simulations, we found that our results are robust and not dependent on the prior error, global prior error values, any mean NE magnitude, or prior NE seasonality. Here we compare our estimates with 3 previous studies assimilating regional aircraft data, one from Patra et al. 2011, Niva et al. 2012, and Jiang et al. 2014. These studies conducted 2 simulations, one with the assimilation of surface CO2 observation, and another study, another simulation assimilating surface observations and passenger aircraft data. In these studies, passenger aircraft data were also from the South Asia region. So these aircraft-based estimates are constrained with regional CO2 observations. And this passenger aircraft data were KEB can control. So these aircraft-based data are constrained with the regional passenger-based observations. And generally, these studies present larger seasonal amplitude, which is generally consistent with our estimates using the OCO2 data. So we conclude that OCO2 data imposes constraints on South Asian NE fluxes in a similar manner as regional in situ aircraft-based data. The most robust signal found by assimilating OCO2 observations was the seasonality. From the strong temporal correlation of OCO2 optimized flux against satellite-based NDVI, EVA, and SIF, and the better agreement of OCO2 optimized CO2 against independent observations, and third, consistency of OCO2 optimized flux seasonality when compared with past studies assimilating regional passenger aircraft-based data, we conclude that the seasonal variability of OCO2 constraint in B is robust, and OCO2 satellite can be effectively used to optimize land CO2 fluxes on a sub-regional scale in a similar manner as regional passenger aircraft-based data. Here we show our current and future efforts with the most focus on OCO2 V10 MIP outputs for 6 years. We are still running those simulations for 2015-2020, assimilating OCO2 and global in situ data. This will help us identify flux drivers contributing to the intra-level variability of regional Indian CO2 fluxes. And we will also explore in future, we will also explore OCO3 satellite, which is on board ISS, and assimilation of regional in situ observations in this global inverse model system. And our future effort will be on developing nested regional modeling effort using the GeoSCM model at an improved horizontal resolution of around 50 km. Thank you.
Thank you, Dr. Saji. It's an excellent talk about that. Satellite data assimilation model. So there are questions I'll give. First one is the Vinu. I was asking you, the withheld of the data for the verification process. What are the criteria and data selection? Are there any rules for data selector verification, or it is a random choice?
It's totally random. It's question by Vinu, right?
Yeah, it means Vinu, can you clarify the question?
Yeah, that is so. You understood the question correctly. Please answer. Yeah.
Okay. Yeah, it's a random selection, and actually it's done by Andy Jacobson from Nova actually. So he did a lot of research on this, and yeah, it's totally randomly selected. I don't think I have any plots for that. Yeah, it covers most of the regions, most of the platforms like aircraft, Flask, and everything. Yep. And yeah, and that withheld data is for I think it's 3 to 4% of the total data. So since it's a random selection, it's a good candidate for an independent evaluation.
Next one is from Pramit. So, while you show that El Nino induced warming reduced the carbon uptake, in 2014 Nature Climate Change showed that warming can result in more uptake due to an apparently longer spring period for the temperate ecosystems. Can you please further elaborate on your results on this context? Means your El Nino induced warming and carbon uptake.
So I think, yeah, El Nino, due to the El Nino, because of the severe drought for 2015, 2018, around, I think even Prabir Patra in his paper found that around 2.5 petagram carbon was released from the tropical biosphere in those 2 years actually. So I don't know whether I understood your question.
Yeah, Professor Philip. Yeah. So actually, there is a study by Trevor Kinnan in Nature Climate Change in 2014, who actually show that in case of El Nino, there is a warming, and that warming actually feels like a prolonged spring period with temperate ecosystems. And if that is a temperate, like prolonged spring, then the ecosystem sequestered more CO2. So that was a widely cited study actually. So I was just wondering, yeah.
This is about the tropical ecosystem, right? So that is about temperate system. That is a different one. So South Asia is in the tropical system where it's already warm. So further warming gives you more CO2 release. If you're a temperate or cool system, then further warming helps the ecosystem to uptake. So there's a different. The difference should be noticed very much. Temperate versus tropical here. What Sajeev is talking about the tropical.
Yeah, I just wanted his view on this. Yes.
Okay.
Yeah.
So I think it's clear. So next is Prabh's clarification of the paper is on biogeosciences. So
that's a minor one. Ignore.
And then Prabhi can ask the other first next question. That is.
Yeah. So that one is more serious, I think. That and then because Sajeev, you get a increased seasonal cycle amplitude, which is of course we think it is true. But I think that the satellites, because the cloud cover, this XCO2 measurements are missing for, not so many for for the July-August time. I think that your peak uptake is coming in September, something like that, right? But I think our aircraft-based data, I think suggests like all the at the end you showed 3 panels with the 3 our my results, Niwasan's results, and the Chinese results. So there you see that uptake maximum is like around August. So that's where also that was the end you showed. Yeah, that one. Yeah. So you see that our uptake maximum is around August or July sometime. So if you miss that July-August month, that means you are missing some uptake signal of CO2 from the XCO2, and that will bias your when you in the beginning you saw the net uptake for net flux for the South Asia is kind of very mild positive. So I think that might happen that you are missing the big sink part, in the XU2 inversions. You have any idea about that?
Yeah, I think we had explored this a little bit actually. So yeah, of course there are less. You can see my screen. You can also see my screen, right?
Yes.
There aren't many observational. There is a seasonality to the observation. In this color number of observations on the right hand side, you can see in this months. Summer months, monsoon months, we have less number of observations, right? So I can show you another plots with the spatial map.
Yes.
And yeah, I think number of observations. It's in a log scale, the color scale. So this is for 2015-2018. You can see more observations in other seasons, and June, July, August we have less observations. But and I'm sure it will contribute to whatever results we found. But I'm also suggesting that in a 4D VAR system, as you know, it's not just constrained by the regional observations around, right? Other observations are also playing a role actually. So yeah, of course there are less number of observations, and that can contribute to some of the seasonal signatures we found in our Earth. So
of course.
But most of
keep in mind. Yeah. Let's move on. Yeah,
that can also contribute to this.
So Sajib, related to this, I have one doubt or question: that how do you treat soil? Is it part of your biosphere, or it is independent, or it remain invariant?
We are in atmosphere, Prasenjit. We don't talk about soil by anything.
Because soil respiration is something which contributes, and it's a part of microbial system, which is also biosphere. And soil microbiome is a big topic, and actually we never understood it so critically in terms of greenhouse emitter.
But our net ecosystem exchange fluxes contain all these processes: heterotrophic and autotrophic respiration, and this ecosystem.
So is there any estimate? Do you have any observation of how much is the respiration variability from the soil from tropical region?
No, I don't have any observations about all these separate components. Even in this this flux estimation system, we are just optimizing the net ecosystem exchange only. We are not even separately finding out what's the GPP versus what's the total respiration. So I don't have any expertise in that soil respiration part. But what I can say is that our total fluxes as an input to the inversion system, we are having soil respiration as well. Actually, all these terrestrial biospheric models are having parameterization for all these. Actually.
Yes.
Dr. Philip, what Prabir and also Professor Ghosh said, I have something to say. So in case of your soil respiration, you are using LPJ. In most of these DGVMs, these respiration components are a certain fraction of GPP. They are not per se model, they're taken just as a percentage. Growth has certain percentage, respiration has 25% of the remaining. So if you are using that, that must be validated against the ground observations. We have a couple of the observations like in Pichavaram and in Assam, in mid-flux India. We'll be happy to share with you. And my second point was regarding to this again. So are your model results validated against any in situ eddy covariance space measurements? The reason I'm asking you, what Prabir also mentioned, that you are seeing the most, you are showing the maximum sink in August, in September and October, if I'm not wrong. And you are showing more source in the pre-monsoon time, the March, April and May time. But we have seen that in case of several forests in North India and Northeast India, that is actually not the case. The most of the uptakes actually happen in August in case of North India, and in May in case of Northeast India. So your results, either of these results might be off, like eddy covariance space measurements or the direct measurements. So maybe the models need to be recalibrated against these in situ measurements. So I had these 2 points to point out.
Okay. Those things can be discussed separately. I think it's a very large topic. So I'll quickly go through some other questions. So one is that Ravi was asking that did you compare this model, whether the model is consistent with other models in the same region?
I haven't compared with any other regional models, but only with the OCO2 MIP models. That's what we were showing here in excuse me, this plot, right? Just with the global models. Maybe the maybe is asking whether I really compared with any other regional models, right? No, I never did that actually.
One suggestion from Binu that IITM having that global ocean air CO2 fluxes near real time from 1961 to 2019. You can contact for this data.
Yeah, sure. It's we'll be very happy to use
and
those.
Shamil is asking, is there any data on impact of L2 XCO2 bias correction or difference between version 9 and version 10 retrievals or flux seasonality?
I think with Shamil, I think most of there are publications from. I think recently we have publication from the OCO2 science team describing all these things actually, this bias correction and a difference between different versions actually. I think I would encourage you to look at 2-3 publications from OCO2 science team in ACP recently.
So I have a question, that is why there is a large difference between this CASA fluxes and your model fluxes, because the amplitude is almost double. What kind of prior flux you are training for your input?
Excuse me. So you mean this?
Yeah, this one. The CASA almost double.
Yeah, the prior flux from the CASA diagnostic model. I think most studies use that one. So, and which is in black. And that's the key result from assimilating OCO2 data. So, some processes within the terrestrial biosphere is causing such a large signal from OCO2. So, my study was about to evaluate whether our signal we are finding from OCO2 makes sense or not. So, in this talk, I was showing you several evidences to support our findings. And in fact, we don't know what the real cause of this large peaks. Right now, we are conducting OCO2 V10 inversions for 6 years, and we will then compare that with different climatic drivers and see what are the drivers causing these changes.
Okay, this is the point that Pramita also tried to clarify, because we need to confirm with our observations that some actual flux observations, then only we can tell which one is whether it's as much flux difference we can expect with the simulation.
Yeah, so
I poorly understood that that's the course, but your model of resolution also it is course 4 into 4.
It's a course.
And 1 degree, but
yeah, that's right. So as I joined in IIT Delhi recently, our effort will be on this actually. So developing more regional modeling efforts. Using the
future maybe we can improve this thing. Thank you, Dr. Saji. It's a very interesting talk. There are a lot of information. So thank you once again for the interesting talk. Over to Binu.
So there is one more talk in the morning session by Ravi Naik.
So we need to take a break, or
we'll take a break of 5 minutes. We can regroup at we can start 12:10. 12:10. Yeah, 12:10. Yeah, and by the time you can check Dr. Ravi's PPTs.
Dr. Ravindra Nayak, are you online?
I said, Rabindra Nayak here.
Yeah. Nice to see you. Okay. Can you please check your PowerPoint so that you can load?
Okay, I'm sharing. Yeah. Okay.
That's fine.
So it is okay.
Yeah, you can go for full screen control V. Full screen view.
I think that is the.
Fine, fine.
Yeah.
Right, change the slides, one slide. Let's see. Fine, fine.
So 2-3 minutes.
2-3 minutes we wait for others to join.
Thank you.
Short break.
Let's see.
Shall we start?
Yeah, we can start.
I will come back. So I'll give a brief introduction about Dr. Nayak. Dr. Ravindra Nayak is a senior scientist at the National Remote Sensing Center of Hyderabad, ISRO. He is working in the carbon cycle modeling and simulation as part of the National Carbon Project of ISRO Geosphere Biosphere program. He is an expert in the even the carbon cycle as well as in the ocean modeling. He is CASA terrestrial ecosystem model used, and he produces as a data he is producing is one project. I know this thing. And today he is talking about that regional carbon cycle model for India and surrounding oceans as part of national carbon project. So over to Dr. Ravindra Nayak.
Thank you, sir. This is Ravindra Nayak, and thank you all. And this is good opportunity for me, given me. So let I go to my presentation. So this is the kind of what I'm trying to tell. So briefing about outline of the presentation and about we have initiated National Carbon Project in early 2010. Then basically at that time there was a measurement of the country was very in comparison to the international scenario, the measurements were very scanty and even if not available that time. And it has been taken initiative, and Dr. V.K. Dadwal was that time director of the National Remote Sensing Center. He has taken initiative to start this project under ISRO Geosphere Biosphere program. And under that certain kind of now we have good amount of in situ data and particularly remote sensing calibration, then upscaling of biospheric informations are available, soil information available. Then what we are trying to do observation, then integrating this data into the modeling system. And what are the integrated model? Morning we have been seen that geoscale and various kind of atmosphere model in practice has been used in together with the fluxes from the ocean and land. And so that regionalizing those regional fluxes through the certain kind of upscaling procedure like the biosphere ecosystem model, ocean surface and ocean biochemical cycle model, and integrating to the geoscheme or similar kind of atmosphere model, so that whatever the data available, those things to be gone to explain the regional, like Indian scenario, really what is the uncertainty, what is the understanding happen, so that those kind of things I'm briefing about that. Then we have like a different kind of strategy followed from the coarse grid to the very high resolution grid over the Indian region, monsoon region. Then we have briefing certain key outcome, what we have arrived at so far on the context of our atmosphere, in the context of ecosystem, terrestrial, as well as ocean circulation. So this is the very old slide I have taken from the when it is the definition has given to the National Carbon Project, and it is this question is known to this community since a long. So that that time that observation was scanty for India, so that certain plan has been made under National Carbon Project. It has assessment of carbon pool fluxes, net carbon balance for the terrestrial biosphere. That was a main focus actually, because biomass till date, also terrestrial like vegetation, like land use land cover map and soil map of the kind of nature available that time, and still there are a lot of problems exist at our end to process the remote sensing data to create those databases. And gradually we have done certain part, and so that we have integrated in the modeling system. And second, to establish observation network like atmospheric flux tower, and like we could see that there that effort has gone. And similarly, ambient atmosphere measurement as well as coastal area, particularly Indian EEZ measurements were scanty, so that is strengthening the establishment of observation network, and then provide support to the and the national communication UNFCCC. What is the uncertainty over India? That was the objective and goals. And some project to achieve that, there are few sub-projects have been defined, and vegetation carbon pool, soil carbon pool, soil vegetation, atmosphere fluxes, coastal ocean carbon dynamics and measurements has been happened, and then integrating all the observations data has come to the carbon cycle modeling simulation. Now I'm talking about much about the carbon cycle modeling and simulation. And this is the one of these slides says that the available data from the like various plot that time it emphasized that time, and sample plot to have like biomass measurements as well as soil mapping that time that has done. And India has good amount of data in the, you see that soil organic carbon content map has been generated, and it is in fact one time, and but it is accumulated period from the certain time 2009 to 2012-13, good amount of data has come, so that it has come, the sample map over the India has come, and that sample again we are strengthening those databases.
Dr. Nayak,
yes,
that is so small, that small window, hide you can click on it, that will go. There is something I'm going to read. The small pop-up is there now, that is hide, you click, it will go.
Okay, thank you, sir. So it is okay, sir?
Yeah, no, it's okay.
Okay, so that you can see that our one of the important effort is from the remote sensing background in the satellite is a land cover map, which is go as one of the input data to our modeling system. So it enhanced the understanding, much understanding. And so that you see that 85 to 2005 different segment people have put the effort from the high resolution data, land use land cover and map has been created for the India. But again, other cycle has come, those who are going to update very soon our nicest portal, and these are the kind of effort has gone. Then this slide particularly summarize that what are the different flux tower across the country we have made, and there are certain flux towers operational, and we have been using certain data to provide the solutions. And then certain new observations also we have recently planned in second phase of NCP project. And this is one of the typical flux tower station in the Haldwani Meerut, and this is the kind of observation available from that day onwards in 2009 onwards. And this data background has come. Then how to synthesize them into a global and kind of unified modeling system. We know that there is a model available, so it has been developed. But again, using these kind of data into that scale to parameterize to the regional scale and to understand much detail, so that we have to go each component one by one. Similarly, this is a schematic of the total modeling setup. We say that it is an integrated carbon cycle model under ISRO IGBP. And in this case, we have taken the geoscheme, which is the atmospheric model, which is the core in the center part, and which is fed to the terrestrial ecosystem model from the left side, which is we have taken again, that is the NASA CASA model. But what we did here, highly parameterized for the regional scale, for regional biomes, and we have done that simulation, then used into the modeling system. And again, this model, the terrestrial ecosystem model, we have done it. If you go to the flux tower station, then you do simulate at the 1 kilometer, even 500 meter resolution to the 5 kilometer. In 5 kilometer grid resolution, we have 1981 to till date the simulation. We have done analysis. And then similarly, ocean circulation, that right hand side was the terrestrial ecosystem. It provides the net ecosystem exchange, which talk to the atmosphere model. Similarly, we have the ocean circulation model. Beginning, we are using the simple parameterization scheme and available data. Now what we did, we have taken the regional model and we are trying to do valid like inverse modeling or trying to simulate Indian EEZ region so that better CO2 flux we can get and so that we can feed into the modeling system. So that we have certain other inventory we are using from the global data, and gradually Indian data can be populated so that we can test various experiments. So this is the kind of modeling scenario in the global setup. When you have run with global data, then we got the global scale at to that time. We have taken the geoscheme 9 version, then we have simulated that and we have analyzed those solution in early days, perhaps 5-6 years back. Then this kind of scenario, if you see that in the left-hand side, it gives a synoptic view of the CO2 distribution. Roughly, it's tropospheric. Roughly, it tells that where are the major sources of the country, who are the culprit, and how the things are moving across the country, like globe. So that basically it is an industrial release coming from the developed country, and it is European and American countries and China, and it is coming to the India. India, in fact, in terms of global, India is per year it is increasing, but in terms of total as a bulk, India is relatively much lesser, but those countries are releasing, and that is most of the atmospheric CO2 is increasing because of that. And this is the what we in that context we analyze the India into 2 parts, northern part and southern part. We simulated in the like whole globe, and we have said that we have flux tower. That time we have only 2 flux tower. Data was available with me. Then I have taken the Betul and Barkot for like Sundarban forest area, and then we have Cape Rama station and the available to the simulate and compare to the model. Then we have taken the here we have not compared flux. We have compared the atmospheric CO2 simulation, and then we see that each that seasonal cycle can be simulated appropriately or not. And so that again, the scale of the atmospheric model to the coming to the scale to the flux tower which measures and Betul and Sundarban, it is like for basically this flux tower measure the footprint area of a few kilometers. But it has also remember of the large scale phenomenon, how much large scale phenomenon versus the regional like local phenomenon that can be seen. If you see that here the certain when data 1:1 when you compare on the left hand side Betul, you can see that from the top when the in terms of mass balance, when you compare in terms of tendency in the trend, like tendency time rate of change of CO2 in the down, you see that we could get even if in the flux tower station the observation coming from the atmospheric model output is very much coming out to intra-seasonal oscillation. And then you see that in the Sundarban area also we have picked up high and low, but except very high up down, that is a marine stations, so that is near to the marine environment. Then when you come to the Cape Rama station, you see that seasonal cycle we could simulate very accurately, even if global model. And when we have to that there is a GHG observation, like Japanese greenhouse gas observations, and then we have OCO2 satellite also operational. Now this particular slide shows that how the GHG we divide into India 2 parts. The 2 boxes I have shown that since the flux tower talk about only the smaller area, but at least the satellite tell the synoptic area. So then synoptic scale are the box average of the northern southern. When you compare, you could see that northern part the tendency of the seasonal tendency. There's a very significant very specific upon like peak and trough you could see. that in the time of here it is September, and it is not absolute CO2, it is a tendency of the CO2. And we could see that there is a season that in September to December to March, this is a positive tendency, and the negative tendency you could see that in the June the peak, and it is started from the March to again May, April. And these two particular tendency, and again if that how the satellite and this together our model is matching. When you come to the southern part, but southern part satellite is not available certain time, but when it is available, two graphs are there, and because that one graph is missing because of data is not available from the GOSAT. But model picking up that, and but if in terms of right hand side, if you see that this is this when you actually they are missing, but when you other data we have taken that which is not missing graded data, we have seen that there is a lot of differences the picking of that amplitudes. But however, the tendency of the model diagnostic, different diagnostic, whether what are the processes controlling the, like whether it is a horizontal transport or vertical transport in versus the local fluxes, we have computed. Then we say that this particular slide summarize that the most of the things, whatever coming from the lateral, it is the out of 70-80% go to the vertical flux, and as a atmospheric phenomenon like horizontal, vertical, mostly balanced. But another 20-30%, whatever accumulated in the system in as a total integrated over the annual scale. In the right hand side table, we have shown that it shows that if India locals local kind of emission, it only could cause not that much. And whatever coming from the lateral, the residual is coming around 80%. That is responsible for the local annual increasing rate of the atmospheric CO2. And this is to say that similarly, we have done the Arabian Sea and Bay of Bengal, and that budget we are about to. We have certain doubt about the Arabian Sea Bay of Bengal because of the kind of model comparison. I'll show you another slide, this particular slide, when you come to the southern side, and certain stations are there available. And those station data, when you compare, those seasonality are not coming that much. But earlier you have seen that seasonality over the India is coming very accurately. And when you compare to those flux tower like observation station, they are the perhaps seasonality are missing some of the stations, and perhaps we have to relook whether those flux we have used in the global model, how accurate are they? And therefore, we have three different globally available flux data available. Then what we see that whether they are how much, what time scale, how they are good enough to believe them. So then we have done comparison, and we have calculated the kind of error estimations, and we think that three different observations like flux data available. Then we say that that is hypothetical true, in fact statistically. Then we have calculated error, and then by solving certain kind of optimization tool, then we see that where are the variance and high errors are located in which area, and corresponding three different fluxes. Left hand side shows that the terrestrial fluxes from the GOSAT flux, and the geoschem flux coming, NASA geoschem flux is coming from the middle error, and NOAA city coming there. And the right hand side, it is about the oceanic fluxes. Then we see that there is a very certain area, errors are very high, and most of them are agreed together, but amplitude of the error, they are of different nature. What we did, then we have combined them, we say that weighted mean, then we have simulated again with the weighted mean as well as all the three different fluxes we use. Then we see that whether they improve or not. That work is we have done. Then here in terms of fluxes, we compare into various stations available to the basically Transcom region, different box we have taken. Then we have looked at how they, at least annual budget, how the different domain they vary in terms of flux. And then in terms of flux, various flux tower, whatever available during our study period we have taken, then compare them. There are certain differences among these fluxes. Then we have use these flux, simulated different kind of model, model analysis. Then we compare them, and we found that there are various different ways they compare. There is a certain uncertainties are there. We highlighted what are the certain uncertainty that we are summarizing. We have not completed still, but this particular slide says that there is a lot of differences between them. And then in that context, that is a global model setup. and global model fluxes. But we need to use our high resolution terrestrial ecosystem model, oceanic model into the modeling system. So what we did, we have taken global setup, then we have done nested grid for the India. Generally, Asia, South Asia, those there is a international team they have created, but we have read that, then geoscheme, we have understood, then we created the Indian nested grid, including, because our aim is to study monsoon and the Indian monsoon region, oceanic flux, those kind of things. Therefore, we have selected this grid. Then, and at resolution of 0.25 approximately, we have created, and then we have to force to, from the global model output, we force to this regional grid, and then we simulated at the 25 kilometer grid boxes. Then we have analyzed, and the below figure shows that we have OCO2 data has come, along track data. Then we have taken the model output, and then we compare them. We could see that again 0.76% correlation coefficient we got here. And there is a certain differences would be there still, but there are certain up and downs or the trough and crest they have been created and captured. And then right hand side, what we showed here, we have two models, one global setup model, one is regional model, coarse grid and high resolution grid. Then we see that whether a high resolution grid can pick up. We have used same fluxes in both the cases, but is there any terrain? Is there any other kind of, without putting those fluxes or regional fluxes? We have used only the global fluxes, but regraded to the regional. Then we compare with the global model output versus the regional model output. We see that there are a lot of improvement happen. And this says that there is definitely there is a good correlation happen with respect to OCO2 as well as GOSA. And even if RMSC, and then if this particular slide shows that we have OCO2, that is we have whatever the time period OCO2 available and GOSAT available, we have calculated each pixel-wise correlation coefficient. This particular slide shows that the OCO2 correlation coefficient nested grid and down is a global model. You could see that the kind of still correlation coefficient has much differences between. There's a better belief that in the nested grid and while the global, there is a global model output correlation little bit less. Then when we look at that, why that differences is there, then we see that this particular equatorial India and other places, how many pixels has been available for the OCO2 data for the comparison purpose. But GOSAT we could not get in the track wise, therefore we don't have that. We say that is a gridded product we have taken. But in the OCO2, we see that a lot of data is missing. Those data are not available. So how much it certain to compare in terms of OCO2 data. So then these are the kind of nested model, but that has been fed with the regional model output of a terrestrial ecosystem model. In the morning, there was a definitely important questions. We have listened that this terrestrial fluxes with respect to soil and vegetation, whether it is properly that the input has gone in addition to the emission databases. This is a natural variability which comes like a vegetation, soil talk to the atmosphere. So that we have taken same terrestrial CASA ecosystem model and we understood that we try to regionalize them. Regionalize in the sense there are certain key parameters specific to the ecosystem types and we tune them with the Indian conditions, with Indian parameters. And then we try to validate at two different scale, at 5 kilometer grid, at 1 kilometer grid. And with again, this kind of model very sensitive to the kind of satellite data, particularly vegetation, NDVI data comes from the, now NDVI is normalized vegetation index, which measure basically the satellite. And as well as there are land use, land cover map, and there is a soil map, soil attribute, which is soil CO2 fluxes, which that particular soil module will be calculating for that. And again, it is driven by the constant to the temperature and the precipitation scalar as well as radiation, all kind of data if they have certain uncertainty, they could create also certain uncertainty, and that need to be validated. And we have validated and published, and you could see that we have district level databases we have taken in terms of net plant productivity. But net ecosystem productivity to validate, and it is very tough task. Therefore, Fox Tower data has been set up, and 4, 5, 6 Fox Tower data has come, and we have compared that that in the one slide you could see that no, it is not there, but we have done that, but there is some differences we got, and we are working towards that and how to improve. And in this particular model, we don't have disturbances factor, in the sense if there is a forest cover changes during the past several years, if there is a kind of forest fire occur, that component as an emission, that is this model has allowed to parameterize and put into, but those databases we are working towards that in future we are able to answer. But without the disturbances, you could see that the down graph, it shows there's a much variability in terms of net ecosystem exchange. And from 1981 to 2005, this particular slide shows there's a lot of variability, and net ecosystem exchange is coming from the positive around 80 teragram carbon per year to somewhere, negative coming to the 80 teragram carbon. So such kind of a variability are there. If it is the variability, it must have the interannual variability of the atmosphere, must be the controlling factor. So that those can be, those hypothesis tests can be done with the regional modeling system. So this is the kind of, we have simulated any NPP and NEP, net prime productivity, which talks about only vegetation, how much it fixes. Similarly, NEP is the how much total soil vegetation, and we have simulated different kind of like 2001 to 2015. How does they vary in terms of trend? Trend in the sense, one way we talk about seasonal cycle, we talk about annual cycle, interannual variability. Other way we look at the systematic rise of the like linear increasing and decreasing rate. And the left-hand side shows that very specific region, there's the increasing rate of the productivity, like vegetation getting more greener and better, and there are certain where the negative side, those area, forest area, they are the degraded, and those response are the negative, and day by day. In the this was done 2001 to 15. In the past, we have done 81 to 2006. And then total, we are updating this. And right-hand side, if you compute the what is the trend controlled by the climate, we see that the climate has very significant role on this kind of tendency contributions. And means the global warming is, and then residual maybe in terms of our fertilization, other effect, what we are doing here, and controlling the irrigation, those kind of things that we are analyzing towards that. And this particular slide says that what is the soil status and soil CO2 fluxes to the atmosphere and soil and forest area. And what we did, one slide beginning, we have shown that we have a lot of measurement during the 2009 to 2011 or 12, then gather a lot of data. We created a soil map. In the top side, that is interpolated those data as it is. Just we have taken the kind of random forest interpolation scheme and we have created. In the down, in the CASA ecosystem model, rather we are putting the soil map into the model. We have started the global model of the soil, initial soil condition. Then we created the 36-year simulation, 3600 spin-off period. Then we created soil biomass and other things like biomass, forest biomass, other things. Then soil organic carbon content from that. Then we have seen that we compare. How are they comparable? They are very much comparable in terms of magnitude, in terms of variability, but in terms of magnitude, there are certain kind of differences are there, and we are going to address that soon. Then in the right-hand side, it is talking about from the 2001 to 2015 simulation, you see that in terms of forest area, how much soil organic carbon content as overall India, it is improving. But when you coming to the cropland, it is improving. But when coming to the forest land, that's a degrading. And means the forest, whatever we see that it is not that forest area is mostly affected, but agriculture area because of fertilizer, many other aspects we have been using, and therefore forest like crop condition is improving, crop area is improving, therefore greening is happening over the cropland. So that particular slide tells this. And this is particularly, as I told, that the ecosystem model is highly sensitive to the kind of vegetation index from satellite. So different era, different kind of satellite coming, and they have the certain kind of biases among them. And then when you use them, before that, we see that if you use them, how much ecosystem response, how they differ. We see that overall in terms of productivity, NPP, they are very much in terms of similar trend, but there is a certain magnitude difference around 20 to 30%. But when you come to the NEP, that's a drastic lot of differences between two different data sets. So tuning of those, again, coefficients, we need more data NEP for the measurements, and we have to go to the field, destructive sampling, those kind of things. It has to plan, or any Indian condition people have to plan, and we have to together work towards that. So that is particular things. Then this particular slide talks about our strategy. We understood that there is a ocean, particularly global ocean data is available. Again, it's a very limited data available global oceanic area in terms of flux. And they are from the very Takahashi. There are a lot of group in Japanese and NASA, NOAA, and the international team, Indian, JAGOPS. They together put a lot of effort and they collected those data. This data being populated, but these data are not enough to see that, understand ocean flux variability, source or sink. We understood there's a sea oceanic sink in overall and in terms of carbon dioxide, but in different segment of the ocean. Earlier presentation talk about, and Patras are also a lot of was talking about modeling and data availability. There's a lot of differences between them. Then what could be the strategy if there's a limited data available for the Indian coastal area, like particularly in most of the coastal area, variability of flux is very high, and they are only the productive area of the Indian in oceanic region. If you go to the deeper ocean, productive area is very less, and they are desert. We say that oceanic desert area. So coastal area, how much Ministry of Science, our National Center for Coastal Research, through their ICMAM project, they have collected a lot of data, and these data are available. Then we got opportunity to synthesize some of the data. Then this particular data has come very, 2008 to 2012 or 13-year period to the Indian, to the collaborative projects by the Ministry of Earth Sciences with different universities. We say that co-maps data. Then this particular Hooghly estuary, and in addition to Hooghly estuary is one of the area where a lot of measurements were available. They have done. But in other part of the Indian Ocean, very less were done. And that has been very individual effort that has been done by NIO and other institutions, though data has come. Our also coastal carbon dynamics project in ISRO GBP, we have other component. We have collected those data. We are working towards how to create fluxes, how to do those kind of things. And therefore, the synthesizing that data to have an Indian coastal area to cover, it requires a lot of effort. Data, not only data, there is a strategy. So the data, again, how much data we collect, that could not be enough. And so that we need to have a kind of modeling strategy, upscaling strategy. For that, and this particular slide tells that with limited observation, and we could characterize, we developed two different models, one for the monsoon time, non-monsoon time. Monsoon, very less data available, therefore we segregated, and non-monsoon time, we have done very good model, and we compare them in terms of scale modeling. It is a basically empirical model from the available observation of various biogeochemical parameter, dissolved inorganic carbon content, and associated parameter. And then there is a relationship between the CO2 content of the ocean. And then CO2 flux is the difference between the atmospheric CO2 to the oceanic CO2, and driven by the various driving parameters, solubility pump we talk about, and in the physical chemistry. So that is driven by the various kind of physical driving parameters. Then we have simultaneous measurement of the CO2 fluxes. We compare them. Then we see that there is a very good comparison model we got. But then it is only the monsoon time, very few observations were there. But how to, this kind of model cannot be applied in other part of the globe, even if other coastal area. We need to have more measurements for that. So that we here a particular slide characterize that whether sink and which that Hooghly area source and sink and how much. Again, you see that data, even if supply data near to the coast is not available. How to fill them? How to reprocess our supply data to bring it better information on that. We have been working on that. And again, whole Indian coast. To have that, then we have a regional ocean modeling system with the biochemical cycle. We have been working towards that. We have looked at in terms of Northern Bay of Bengal. We try to simulate current and various biochemical parameter. We understand that we are in the job, and we have not complete answer towards that. And we wanted to integrate this for the Indian EEZ area. And so we are in the job so that we could answer certain things. But important, how much data we collect for the Indian coastal area, and how there is a people have collected, how to get data together. And perhaps IITM is very central point, and people are working so that we could make some kind of cohesiveness to have making the data, regional data with upscaling procedures to kind of modeling and to RS-based modeling and to the dynamic modeling like regional ocean modeling system, like inverse modeling give the different kind of solution. But forward modeling gives you, like, if you have more data, you can reach to the more reality, more understanding, and you can better give. And for inverse modeling, otherwise, if you don't know, it will give, but it will give you path to know. You go and collect the data, so that the data collection is very much important. And with this, I think I complete my presentation, so that this is the future scope and goal. And particularly National Carbon Project of ISRO GBP has very much encouraging to participate other department to have a collaboration. We can work together in terms of improving the data quality and collecting new data sets, and particularly remote sensing upscaling procedure. We have satellite data, certain experience, lot many groups are available with our group here. Beginning, I told that vegetation carbon flux, soil carbon flux, and there is a working on the coastal carbon dynamics measurement, atmospheric measurement. Our Mohesh is very much strengthening his observation system, and carbon flux tower. We have maintaining 4 or 5 flux tower, and we can collaborate and exchange our data with the other, like our IITM. So how we can go together to have improve the understanding, and particularly terrestrial ecosystem, oceanic ecosystem, to improve the better flux, so that tomorrow we can give better answer. So that I thank you very much for giving me such opportunity, and I'm very happy to, if some questions could come on that to answer. Thank you very much.
Thank you, Devendra. Very interesting talk. It's a lot of update about national carbon projects and its their CASA model outputs. So in this, we have enough time for discussion also. So it is a question from Meher. Just compare. Is it okay to compare the measurements, flux measurements from a single station over North India and Southern India for a satellite retrieval?
Yes, very interesting that actually we have got, but we have also a few more flux tower data, and we are getting that we have 5-6 flux tower operational. And to address, like last 6-7 years, we got at least interannual, also intra-seasonal, we can explain variability.
Yeah. So next is from Vinu. Vinu is a suggestion. I think it's can you clarify that your comparison with intra-seasonal oscillation on geochem and with Ravi's paper, I think.
Yeah, thank you, Ravi, for a very nice talk. They are doing a lot of effort in geochem downscaling of high resolution features of carbon transport, and that show the tendency of carbon concentration capturing high level of intra-seasonal signal, which is inherent of the Indian monsoon system. So it could be a good point how geochem's performance can compare with the same features observed from the tower data. Ravi Kumar has published similar work. So also fluxes also show similar intra-seasonal signal both in GPP and respiration. So this can be cross-compared with this geochem high resolution. That's just a comment. That's all. Thank you.
So this is a very encouraging thing. Important is that actually, even if within our group, data exchange is one of the big problem of getting data and seeing. We are struggling when we have did the modeling front. We have done a lot of, the inverse modeling, how much you have done. It can be done very easily, but not with a certain difficulty, in fact. But observation, sharing, and working together is one of the big issues. And thank you very much. If those data could be shared and we can work together, and we can improve the quality of the terrestrial influx and those kind of things, and particularly ocean also. You are very expert on that. We have started, and we are very much enthusiastic and to work, and so that it is a very good opportunity and platform.
Yeah, data exchanging policy yesterday we discussed in the panel discussion, and we are coming up with more strategies and improving that gray area, how to meaningfully exchange and collaborate among various
model
institutes.
data can be shared. Suppose I have done some hypothesis I can do. I can give the data, and you are like that who is collecting data, they can write on that, so that it is also can be done.
Exactly. We had extensive discussion regarding that. We agree with that. True. Thank you.
Thank you.
I have some clarification about your CASA model, biospheric model.
Yes.
So you have done some 30 years simulation. This is data availability in monthly scale or daily scale you have done?
It is available. It is for the flux tower specific. It is we have done diurnal scale for few flux tower and station at 1 kilometer grid. But for the whole India, we do that monthly scale from the day, like in 1981 to till date.
You are used to that modest classification or Boban classification for this?
So we have that in that CASA has a, like, that is a kind of classification, USGS classification 12 classes. We parameterize those data and those things for our area. We have an agriculture expert, we have forest expert. We took together a lot of effort, and we have done those tuning of those parameters for, and broadly India can be classified out of 12 classes.
The tuning means that lambda, alpha, that beta, that parameters are tuned for Indian region?
Those efficiency parameters, CN ratio, and related other parameters of the ecosystem types, they have been parameterized, like we taken for India. And it allows to, if there's uncertainty like Q10 factor, for example, soil respiration. And that Q10 factor for certain ecosystem are defined, we have taken from the global literature. And we have also flux tower, like soil flux tower, flux measurement. We have put many places our soil, like agriculture as well as forestry location, that data has come. We are tuning those parameters and to have a better soil flux exchange, as well as forest also we have selected agriculture land flux exchange. Those things may be coming up and we are integrating. When they publish, then we take those things.
Did you compare with your products with the CASA they are giving from their site, their website?
We compared last IITM presentation 3 years back, we have gained like inter-comparison between that, because global give very a broad scenario, and you are lot of deviations from that. You are there. That slide is not here, but
okay.
There's
but you found some differences between the actual CASA model from their website and your simulations.
Exactly, because that is the global data they use, and they simplify many things.
Okay. So there is a comment from Prabir that
yes,
time derivative. I like the time derivative time fluxes. So how is it different from seasonal cycle of subtracting the trends?
I cannot get again, please, sir.
How the time derivative of flux time series in different seasonal cycle. Yes, Prabir, can you clarify this thing?
Can you go back in your slides? When you compare the flux tower sites and many flux tower sites we had, and then you are comparing the
two flux tower site I compare. Yes, this slide we're talking about.
Yeah, this one. Yes, sir. Please. It looks interesting, but I'm still confused. How can you get this kind of comparison with the CO2 concentrations? Right, this is CO2 concentration, right? In the
comparison with flux tower, how much intraseasonal oscillation it is picking up?
Yeah, so I cannot get the whole picture, because here you are so what is the red and black? What is the red and black lines?
I'll explain. So in each station there is a tree plot from the top to bottom.
Yeah.
You have that in the as it is ppmv, like in the volume unit. So you have the data that black is observation and the red is the model output.
Yeah.
And then the down when you convert it into the mass unit.
How do you convert that to mass unit?
Because in the flux tower station, we have the temperature, all the data we have, because in the volume, you can convert it to the mass, because everything is in mass unit. Conservation applied in the mass unit. When you, am I able to convince her?
And anyway, go ahead.
And then that is a mass unit. In the second one is the mass unit. Obviously, it is almost similar, but you see that the drop down it has come when mass in terms of mass. And clock tower actually measure that in terms of millimoles per cubic meter mass scale. And we have a different units. So that beginning we have in the volume unit, ppmb, then millimoles per cubic meter. Then we have converted in the mass in the equation. We have the mass change of the mass in terms of kilogram or gram per cubic meter per month. In that scale, we have taken our model steps. Then we have simplified, filter it for the daily scale, and then because model simulate at our 2-hourly interval. And then we have taken it for the daily scale. Then we have applied certain filtering technique. And so then we say that how much the answer, variability can be comparable. This is that. The tendency in the time rate of change down, it is a mass change per unit time, like left-hand side of the mass balance equation. Am I, sir, able to convince, sir?
For example, I'm still for example, your in the Sundarban data, the top panel goes to much farther in time, but the next one does not go that far.
Sir, the first one is in volume. Volume basically when atmosphere expand, let's say if temperature is higher, moisture, it controls the density field, and obviously volume also changes, air masses. And but when you convert into the mass, if you have let us say you don't have the fixed, let us say you have fixed box, then only you can take how much mass. But since the atmosphere is highly compressible, so it is better to convert into the mass.
Anyway, I think we should talk offline, but if we other people understand, I think it's good for people to understand this figure.
Sir.
Yeah.
Sir, thank you.
Sir. So is there any comments or questions to the Bint? Is there any more questions? You can thank Dr. Ravindra Nayak for a wonderful talk. So,
thank you very much, sir, giving me opportunity, and thank you IITM and international team to giving me opportunity.
Yeah. So over to Vinu, so you can.
Okay, thank you, Dr. CG, for chairing this session very nicely, and we had all 3 good talks, excellent talks. Excellent information. We are ahead of time. 5 minutes we still have if the members want to discuss or the attendees want to, or maybe we can ask them how the training session going on, because we have 10 minutes still available. So the attendees wants to feedback about the training program that you attended yesterday and the day before, then you can do so here.
Sir, Binu, I think even the people who are giving training, they can also speak.
Yes, they are also here. Yes. Let me check. I think Rakesh is here.
Whatever. I mean, whoever wants to talk,
permission to talk.
Both sides is okay.
Let me bring them up. Pramit can brief yesterday how the training went, and participants can also comment. Pramit, are you there? I think Pramit is not there. So maybe we can ask this question. But this is the time we
why
see.
Not ask participants directly?
Yeah, participants can, but we can't elevate everybody them to speaking, but they can type.
They need some permission to talk. I think some people don't have permission, attendees.
I mean, none of them are given permission to talk, because otherwise this session become very clutter. Yeah. So please type in the chat. Even panel members are typing in the chat only. So we look forward to your chat. I think they start typing now.
So maybe you should ask Subhas first, what do you mean by too good? Yes. Too good means what?
Can you elaborate what is too good?
What is too good?
Yes, that's right. What is too good?
Excessive use of adjectives, or you really mean it?
we expect some criticism.
Yes, exactly. Too nice means you cannot do anything anymore.
So no
I
response.
think it's very good if we allow them to speak.
Yeah, I think so.
Let me
Yeah,
check with
that's
our
right.
team members how quickly they can convert it. Give me a second.
Yeah.
Sir, better we can ask them who wants to speak, and then we can start unmuting them. So they can raise their hands, whoever wants to give their feedback.
Yeah, they are converting everybody into speaking mode. So it will take maximum 30 seconds. So then they can speak. We'll wait for that.
Okay.
One Saurabh said training was comprehensive with good mix of theory first and then practical. I wish it was a 2-day session. I was new to it. Okay, they'll want an extended training. Smrati Gupta says all the lectures were interesting and useful to early careers. So far, the training has been comprehensive, consolidated lectures in the field of observation and model studies. So I think most of them have given now speaking privilege. So you can speak now, unmute your mic and speak up. There's a raise hand. If I is found, I will call that name.
Hello, Professor.
Yes.
Am I
Who
audible,
wants to
right?
speak? Yeah, you are audible.
Yes, my name is Mihir and I'm from Ahmedabad. Actually, thank you for organizing this workshop. Actually, I'm very new to this field. I just completed my undergraduation this year. So, talking about yesterday's, tutorial session on eddy covariance method. So it was actually, well balanced and well mixed of theory session and tutorial session. Because first we introduced to the theory part of eddy covariance method and different, flux measurement, how flux measurement can be done, which are the instrument and ADAR generation and all. Then we introduced to the, actual, the tutorial part where we get to know the, about the model, we can use eddy pro model and all. So it was well balanced, session. I will look forward to having more this kind of session in this workshop. Yeah.
Okay. Anybody wants to note a critical improvement aspect of this training, then you can suggest. We look for points to improve. I appreciate appreciation, but are there any points to improve or something that you want?
One thing I meant, I want to mention that if you, in this modeling workshop, if you could introduce, the current PhD or postdoc student to present their result in the field of GHG modeling and all, that could be a good point, I believe.
Okay, Prabir, what do you think about that? They want some opportunity to highlight their own research in the field.
Yeah, last time when you're in person, we did those kind of things, but yeah, this time it's online, so that's a problem.
Correct. Last time we did a group team,
yes,
we teamed them into groups, and
yes.
each groups were asked to present.
Yes.
That definitely is lacking in this online mode.
Yes, it's very difficult to manage
it. Not easy. Yes, people are from different places, so.
Yeah. So, but yeah, it's a good suggestion. But then, so one thing is here that it's not everybody's same, right? We have there is a lot of difference in the participants. Like some are very newcomer, some are like having high research towards the end of their PhDs, or even young scientists. Some places, right? So it's like always difficult to give individual chance. Yeah, but yeah, we can do the group again next year's. Right, Ravi, Vinu?
Yes, I completely agree with that. That definitely. Yeah. Any comments from the attendees about the training session? Now all you can speak, you unmute and you can speak. Or you can raise hand and I can call your name. Imran has raised his hand. Imran, please.
Yeah, can you hear me?
Yeah, we can.
Yeah, of course. I was in the panel discussion, but after that, somewhere I was, keeping watch or attending the training session. What I feel is, like as Prabhi sir said, it is a wide spectrum of student. So whatever is going in the training or in the hands-on is very good. Like those who are the newcomers, but those who are a little bit into the field, for them we can do some improvement. For example, like a little bit of doing some calculation or giving some exercise, like how to do some, let's say, with the raw data of eddy covariance system, estimate the flux rather than calculating it from given software. So such some exercise or some programming hands-on, that would be the next step. This is what I feel.
ठीक है.
Yes, I mean, these were all there last time around, the last two ones. We actually even ran inverse modeling in the first workshop. So, yes, good suggestions. Yes, it's a good point. But one thing for sure, for example, these workshops have a wide variety of topics. So, for example, somebody working on the eddy covariance, he would not know about CO2 concentration management, or even observations of CO2 observation and concentration, like the precision we are talking about. So I think there is always something to learn, that not everything will be like in your level, but I think there is something always there to pick up from. And it widen your horizon in terms of knowledge.
I have one point to note. This in respect of Imran's question. Actually, eddy covariance training, it takes minimum 3 days. And in IITM also arranged such kind of training in the past. And this workshop actually gives a flavor what eddy covariance technique is and what we can do, what we can learn. So just to give a flavor, and so that people get interested, and then when they get into this project, this kind of work directly, so they can learn elaborately. So very comprehensive training. It is not that problem.
I do.
So for that you.
Completely.
Yeah, we had eddy covariance exclusive training in IIT maybe 4 years ago.
Yes.
And with the national, international
Right. Yeah.
4 days, I think it meant theory, discussion, a lot of debates and all. It was very exciting. So yeah, maybe we should focus on not the GHG as exclusively eddy covariance. We'll come back to that point maybe sometime. It's a good thing. One student replied that, I don't know, student or scientist, Sanjukta Ghosh, I did not have any knowledge in the GHG field. This workshop helped me a lot in understanding the GHG also. So that's a good point. And Smriti Gupta from IITM say, I feel eddy covariance theory and demonstration is a big topic to cover in 2 hours. That's true. That's what we are also discussing. Yeah. So other participants, if you have any comments about the training, you can express it here. We'll close this session in another 2 minutes. So if you take the mic, it will continue or we'll close it soon. I think there are no more comments. So let me close the lunch, post pre-lunch session here, and we will regroup at 2:30 for the post-lunch session, and see you then.
Okay. Please remove the message that MS Teams is not working. Sorry.
Harjinder, are you able to log in?
Not
yet.
in. Not yet. That's what I am looking at.
Yeah, she will come because you already told her and she acknowledged. She's already awake. You mean?
Okay. Oh, this is he or she. Harjinder is he or she.
She.
Oh, okay.
Yeah. Because she has logged in
to the presenter mode.
Yeah, she has logged in. You can find, right? So she has logged in already, and you can see that.
Prabir, can you read out the name she logged in?
Harjinder. Something.
Okay, I can't see it. Maybe our team will see it.
Yes. It should be Harjinder or Sembi. In the case, Sembi or Harjinder, one of them, or Harjinder Sembi. Can they see it?
Okay, I think she's in,
Okay.
but I can't see the name in the list. But probably, are you seeing it, Prabir?
And I don't see that too.
Okay.
In the presenter list, I don't see.
Yeah, me too. Hello, Dr. Harjinder, can you hear us?
She cannot talk or show anything video. She cannot talk, she says in the email.
That must be old email, but just now we upgraded her to the presenter.
Ah, yes, now you see her. Yes, now you see there. Okay. Yes, there you are. Good.
Okay.
Hi, apologies. I think it was my VPN wasn't allowing me to join the meeting.
And also, like they have a two-layer system here.
Ah, okay.
They have to promote you to be presenter, then only you can speak or.
Okay, okay, that's fine. Thank you.
Good, great. So you may try to maybe.
Thank you. Right, let me share my screen. Let's go for that one. Presenter mode. Okay, can you see my screen?
Yes, it's all set. It looks all good.
It's in full screen. Okay, fantastic. Yes. Apologies for the delay in joining you.
No.
I think my university VPN was being a little bit strict there. Right. Thank you for inviting me to join your national workshop on greenhouse gases. This is a joint talk by.
I think just hold on. I think they will start the.
Brilliant. Okay.
There will be a chair and then there will be all the things moderators.
Excellent. Thank you.
So all else is good and Harmut is doing well, busy and.
Harmut is pretty busy with teaching and examinations. Yes, and we're all in lockdown again as well, pretty much.
Yes. That's a pity, but I think we cannot do anything other than that.
Hi, Dr. Harjinder.
Yes, we know.
Hi.
Hi, how are you?
I'm very well, thank you.
Yeah. Okay. So, Prabir, I think we will wait another 2 minutes if possible.
Yeah.
Okay.
So who is chairing this session?
And I'm chairing the session. I'll introduce her.
Okay, good.
Although I don't know her much. I don't know much about her, but I know Hartmut. I'll explain their group and please introduce Harjinder after that. Okay, help us.
Yeah.
Thank you.
So Harjinder also, by the way, I think she's going to talk about greenhouse gases today, but she also works a lot on the air pollutions.
Okay, so we are good to start. Dr. Harjinder, are you ready?
Yes.
Yeah. Okay, so good afternoon and welcome back to the post-lunch session of this workshop today. And today's keynote talk is planned to be delivered by Dr. Hartmut Bosch from University of Leicester, UK. But as he was occupied in other activities in the university, he asked his colleague and postdoc, Dr. Harjinder Shempi, who is with us today to present. And Bosch group is actively involved in the remote sensing of greenhouse gases, especially he was part of this NASA JPL team of OCO in the early stages. And then he established a lab of his own in University of Leicester, maybe in the late 2000. And his colleague, Dr. Harjinder, is also a specialist in air pollution monitoring. And so I welcome Dr. Harjinder to present on monitoring emissions of greenhouse gases from space, from global to local scales. So over to you, Dr. Harjinder.
Thank you, Vinu. Thank you again for inviting me to join your workshop on greenhouse gases. This is a joint talk by Professor Hartmut Bosch and myself. So I'm an Earth observation scientist. I currently work in the School of Physics and Astronomy in the University of Leicester, but I also work in the Department of Geography at King's College London. And my interests are mainly sort of land and atmospheric interaction. This is looking at agriculture, productivity, air pollution, and sort of greenhouse gas emissions. I'm very interested in working with Indian colleagues to understand this from an Indian perspective. And so, as you mentioned, at the University of Leicester, and through a lot of the work led by Hartmut, we have been developing satellite retrieval algorithms for greenhouse gases from a suite of satellite sensors. And today I'll just present to you a short overview of the current remote sensing capabilities and the challenges in observing greenhouse gas emissions from space. I will then show a range of case studies, some of it relevant to the Indian perspective, to help us understand and monitor greenhouse gas emissions from the global to local scales. Okay. Okay, so it would be right to start this talk by showing you one of the most important data sets we have for atmospheric carbon. And this is, of course, the Keeling curve, which is the longest continuous CO2 measurements that we have going back to the 60s from the Mauna Loa Observatory. And the importance of this data set is that it unambiguously demonstrates the increase in atmospheric burden of CO2 is due to human activities, which, of course, is now increased from a pre-industrial level of about 280 parts per million.
Yeah. Actually, we cannot see your slides. We are seeing you.
Actually, we do see Prabir. We are seeing the Mauna Loa curve on our monitor.
Good. I cannot see you. Anyways, okay, go on.
Okay.
Prabir, I recommend Prabir to log out and log in again. That will help.
Okay. Fantastic.
Okay, go ahead. Thank you.
Okay.
Sorry.
That's okay. So obviously, just going back to the Keeling curve, what this shows is that we have added more than 200 gigatons of carbon into the atmosphere, which of course is a great concern because CO2 is an effective greenhouse gas leading to global warming. And so if we look at the underlying carbon cycle, we can see that it's a dynamic, it's a live system. And this is, for example, shown by the regular seasonal cycle, which is due to photosynthetic uptake of carbon by plants during the summer months. And of course, this has a relatively small but a noticeable amplitude of about 3 to 4 parts per million in the Mauna Loa measurements. And this, of course, would be much larger if you were in the middle of a forest. So we can see that there is an increase in the increase is continuous, but it's not constant. And we have a large year-to-year variation in the buildup. And it's this atmospheric buildup that's a result of an imbalance between the sources and sinks. And yet, we understand that there are many variations in the sources and sinks. So we can have a look at what the differences are in these sources and sinks. So in terms of the sources, we of course have emissions from the combustion of fossil fuels and a modest contribution from land use change such as deforestation. And these emissions are of course emitted into the atmosphere. However, it's only about 46% that remains in the atmosphere, while the other 54% is taken up by land and ocean ecosystems. And what is really remarkable that the airborne fraction on average has remained astonishingly constant. And in the presence of the increasing emissions, this implies that surface sinks are growing with these emissions, but it's still whether these will remain constant in the changing climate is unclear. So already we can notice that on a global scale, there is a fraction that we just can't account for. So after many decades of research, we are still faced with fundamental questions on the carbon cycle and how it couples to climate. And a lot of these are related to understanding the sensitivity of land carbon fluxes to climate, to understanding the change and variability in fossil fuel emissions. So what about methane? Well, of course, the situation is even worse for methane. Although it's similar to CO2, methane concentrations have again increased quite significantly from pre-industrial levels. But the atmospheric buildup shows a very significant variations that we can't explain at the moment. Because if we just look at this graph, we can see that in the 90s, we had a slowing down of the growth and a period of stabilization in the early 2000s. But in more recent years, we've seen an increasing trend. And the difficulty with methane is that it has such a large number of natural and anthropogenic sources, and it's really that we don't really understand many of these well. So the growth that we see in methane is actually an imbalance between the variable and not well understood sources and sinks. And there's still a large debate about whether the stabilization and recent increases, and of course there are many different explanations that have been put forward, such as the role of wildfires, increase in natural gas and coal use, and perhaps more wetland emissions. So these are some of the questions that we have been looking at. So why don't we have a look at the role of atmospheric measurements? The atmosphere is, of course, a very powerful integrator of surface fluxes, and it's the concentrations and the gradients that we observe that have an imprint of these surface fluxes. And this is what provides, for instance, a very strong constraint of surface fluxes when we use atmospheric measurements in conjunction with transport models. This is a well-trusted approach, but obviously surface networks that we use so far might be too sparse and uneven to inform us beyond continuous scales. And what we really need are observations that are dense, are frequent, continuous, and everywhere. And this is where satellite measurements come in. We, of course, have almost continuous greenhouse gas observations since 2002, when we had some of the first shortwave infrared measurements made by the Skiamaki instrument on Envisat. And the shortwave infrared is very good because it has sensitivity near the surface. Moving on to new satellites like Sentinel-5P Tropomi, these help us provide a way of diagnosing strong methane emissions sources quite distributed globally. However, we do have an issue sometimes with the coarse resolution that some sensors give us, and this can be a major limitation depending on the type of greenhouse gas observation that you want to observe. So to counteract this, there are many new and upcoming hyperspectral missions, for instance, which have great potential and offer much higher spatial resolution than Tropomi, for instance. And this is just a nice chart showing some of the different resolutions for some of the future missions that we should be able to work with. Of course, it can be a challenge to observe greenhouse gas emissions from space. And there are some observational challenges that we have with some of the satellites that we use. As CO2 is long-lived, the signal that is caused by the surface fluxes can be small, typically only a few parts per million out of about 400. So that's only 1 to 2% of the total. We also need to be able to observe this signal with relatively small errors, and this means that we need to make the observation of CO2 much better than 1 ppm. This is quite a big ask for the remote sensing community, especially as what we will have to do is make these measurements using sunlight, where the light path that we have to use to observe can have quite large variations from scattering. This can be due to aerosol scattering. And so if we want to succeed in doing this, we have to design an approach that allows us to obtain information about aerosols as well as CO2 together. So the approach that we use by the work that's done by Hartmut at Leicester is to combine 3 spectral bands together. So this is combining the co-located CO2 spectral bands in the shortwave infrared with an O2 aerosol band that's located at 0.76 microns. And as we mentioned earlier, this is part of the work that Hartmut developed as he was part of the original team that helped develop retrieval methods for the NASA orbiting carbon satellite, orbiting carbon observatory mission. And this approach is quite sophisticated because it combines a forward model with Bayesian optimal estimation method, and it extracts a full set of atmospheric and surface parameters simultaneously. Oops. Right. So one of the issues can be with this sort of approach is that you have to have a fully multiple scattering radiator transfer model, which is sometimes not feasible to use, and it can sometimes be much too slow. So we need to find new methods that allow us to speed up our retrieval process from satellites whilst maintaining the retrieval accuracy. So one of the methods that we've been working on at Leicester is by using something called the principal component spectral binning method. And this was some work done by our previous PhD student, Peter Somkuti, who is now a mission scientist at Caltech. And the key idea here was to use a redundancy in the optical properties that we observe in the atmospheric spectra. And by using this PCA-based approach, we can do this with a lot more accuracy than sort of generalized radiator transfer. And the key advantage here is that we can avoid some of the errors that we might get for certain things like large aerosol optical depths, whilst also gaining a speed of up to 100 in our retrieval process. So by combining all of these sort of retrieval approaches that I showed you, we've used a lot of these approaches for a large body of work that we do at Leicester, which is focused quite strongly on the Japanese GOSAT mission. And this is really to generate long-term, continuous and global data sets of greenhouse gases, as shown by the 2 left-hand panels here. We have the full physics CO2 retrieval and, of course, the methane proxy retrieval. And as well as that, we also look at other greenhouse gases, which include boundary layer water vapor and new types of data sets, such as water isotopologs. And what's really nice about using GOSAT is that what we want to do is develop a long-term climate quality data record. And some of this data has gone into programs such as the European Space Agency's Climate Change Initiative and the Copernicus Climate Change Services programs. And this is a nice little example showing how our GOSAT, CO2 and methane data sets have been part of these programs. And some of these data sets have been combined with older greenhouse gas data sets, such as those from Skiamaki. And what's nice is once we combine all these data sets, you have almost 20 years of information on greenhouse gases. And these are the timescales where these data sets become even more valuable because they can help us evaluate long-term sort of climate models. So I'll just take a little sidestep to say that one of the other novelties that we can do with some of this data that we look at is we also have a way of tracking directly photosynthesis from space. So we know that when plants absorb light to synthesize sugar from CO2 and water vapor, there is a certain fraction of the excess energy that they need to get rid of, and it does this by emitting light. The signal is very small. It's only about 1% compared to the reflected sunlight, but it can be measured by satellites like GOSAT, and we can do this because it infills some of the solar lines from the emission that we capture from the surface. And this is actually quite an interesting and a nice addition to some of the CO2 retrievals that we do, because we have to retrieve it, because if we don't, and if we don't correct for it, it would actually cause a bias in our CO2 retrieval. So what's nice is that by retrieving this, we can actually even generate its own product of solar-induced fluorescence, or SIF, from the GOSAT emission. And it's from this signal that we've been able to create these maps of the global distribution of the productive regions around the world in terms of agriculture and vegetation, and we can understand their dynamics, and we can understand something about the taking up of carbon from photosynthesis. So what's quite exciting about the SIF information here, that it actually provides us extra information about CO2, because SIF is related to only one component of the carbon exchange. And so here's just an example of what some of the SIF datasets look like. But even when we're looking at slightly quite coarse satellite measurement scales like GOSAT, we can see that SIF, when we look at these larger scale, tracks very well with the gross primary production, which is a way of finding out which is a way of understanding the photosynthetic uptake from plants. So here is one case study that I want to show on this particular subject. So this was a case study done by Peter in his PhD thesis, and this was, the example was that he was looking at was drought in the USA in 2012. And obviously we know that droughts are expected to become more frequent in the USA, especially with global warming. But there's one drought case in particular that he looked at, which was 2012, because it was the most extreme drought since the records began. And it led to about a 30% drop in the crop production for that year. And these sort of short time climate extreme events are interesting, as it allows us to study the response of the entire system to the changing conditions. What was very unusual here was that there was an early spring onset of the crops and the agriculture due to high temperatures. And this was exacerbated by the trop conditions, which then went on to deplete water reserves. And so by combining SIF and CO2 anomalies here, as shown in these sort of panels here, we were able to diagnose the signals that we see in SIF, but also CO2 fluxes, which basically the CO2 fluxes describe the respiration and photosynthesis processes. And the CO2 flux here was provided from a flux inversion with the GHG-3 model. And what was quite exciting to see here was that SIF as well as CO2 fluxes both showed consistent early onset and a reduced productivity due to the drought. And once you have both of these parameters together, we can have some handle on the processes. And now these are the sorts of things we're using to help us diagnose other land surface models. Again, here's just another example showing how CO2 from satellites can be used in conjunction with SIF. This is quite a nice study that was recently published and led by our National Centre for Earth Observation colleagues in Edinburgh, namely Paul Palmer, who I think is speaking tomorrow. So in this study, they used the GHG model to do a surface flux inversion using GOSAT and another sensor, OCO2. And what we found in this study was that GOSAT and OCO2 data were both consistent with each other and pointed to a much more enhanced seasonal cycle over tropical Africa with a much larger net emission signal. And what I think was happening here was that the largest carbon uptake was particularly over the Congo Basin. And there were two loci of carbon emissions over the Western Ethiopia and the Western tropical African regions. And what they think here, what was happening was that there was a large soil organic carbon stores, and these were because there had been substantial land use change in this region as well. So this is the sort of reason for these larger CO2 fluxes from the soil and land use change that they saw in this particular inversion study that they did. So if we think about CO2, of course, we've also done some application of the methane data that we've been looking at. And as with all satellite data sets, it's really important for us to assess the quality of this data in many different regions of the world. And this is especially critical for tropical Africa, because it's a region that has quite a high aerosol loading and, of course, plenty of clouds. So this is some work that my colleague Neil Humpage did. And he went to Jinja in Uganda and he installed a new portable Fourier transform spectrometer. And this has given us a really nice opportunity to overcome some of the limitations that we have in assessing greenhouse gas satellite retrievals in this region, but also it gave us an opportunity to collect and analyse this complementary data set. So this is just some work that Neil is preparing for publication at the moment. And here Neil was able to compare the ground-based FTS greenhouse gas measurements and also made an assessment of various satellite observations, as well as including some model data sets that had assimilated satellite data sets. And these are shown by these two time series here. So the top one is for CO2 and the bottom one is for methane. And the time period of the data collection covered the dry season as well as going into the wet season in tropical Africa. And what he found was for CO2, they got very good agreement during the wet season between the models, between the FTS and he found quite good agreement during the wet season, but he found also that the models and OCO2 tended to underestimate the values in the dry season. And this was a little bit surprising because the expectation was that the models and the satellites might do a much better job at reproducing the CO2 levels during the dry season. For methane, they actually found a reverse, and they found that there was much better agreement of the FTS measurements with Sentinel-5P in the dry season, except when they had fire events. But they also found that there was more of an overestimate from the satellite during the wet season, and this would point towards an overestimation of wetland emissions in the satellite measurements. So sort of sticking on the issue of methane, here is another area that some of the work that HeartMath has been doing is focused on, and this is particularly in the Amazon. And so again, we were specifically interested in wetland emissions. And of course, the Amazon is home to very large wetlands, which can be very large contributors to the global methane budget. So this was some work done between a joint UK and Brazilian project. And in this work, the team flew a local aircraft that was equipped with in situ samplers to obtain profiles of methane. And these profiles were then compared to satellite data sets. And it was actually quite a nice project because it gave those of us from the Earth observation community to actually have an opportunity to get a true impression of the system that we study with satellites. So major strength, of course, of satellite measurements is their ability to map out the regions and show nicely this spatial distribution. And what these figures show on the left is simply the difference between the wet season and the dry season. And this helps reveal the seasonal component of methane cycle, which is essentially showing us how the wetlands are changing. And what we see on these figures, these sort of panels on the left-hand side, is enhanced signatures of methane over the Pantanal region, which is actually one of the world's largest wetlands. And we see, for instance, specifically very large enhancements in 2011, which was a wet year due to the influence of La Nina event. And so what we have been looking at is whether one of the sort of key questions is if we have wetter years, will this always lead to more methane emissions? So these are some of the things that my colleagues are working on. So sticking to the Pantanal wetland region, here is some more work done by my colleague Rob Parker. And in this work, he extracted the wetland signal in the satellite dataset and looked at data from different models using different model runs where the wetland emissions were removed. And what they found were characteristic enhancements for some years that were not reproduced by the models. And in his work, he found that almost some models missed up to 50% of the seasonal signal of methane over this region. And to better understand some of these features, he looked at data. He looked at some data from the NASA GRACE satellite, which is a satellite that measures the gravitational field of the Earth. But as a byproduct, they can also determine the total water storage anomaly, which is a really nice approximation to understand the changes in the wetland extent. And so what he did here was look at anomalies in the GOSAT methane with anomalies in the GRACE terrestrial water storage. And what he found were that these anomalies coincided with very large but local flooding events in the river-fed wetlands. And the process that was causing this was overbanking inundation, where the water was transported downriver, which then would lead to flooding. And what he found in this work was that the models were actually missing this quite important process. So it's the absence of this process in the models, which meant that a large proportion of the methane emissions were completely missed by some of the simulations. So this was a really nice piece of work, and it's really important because it shows that there could be certain impacts for future climate forcing that are currently not accounted for in some of the models. So that's looking at sort of natural processes. Of course, we are also interested in understanding other things like emissions from country levels to better understand some of these different emission sources and the uncertainties. So here are two examples that Hartmut was working on. So this is working with inverse modeling groups from Harvard and Bristol. And so the first example is at the top, and this example focuses on the USA. And what they found here was by using, basically what they did was use GOSAT methane data in conjunction with in situ data and sort of high resolution inverse modeling. And for the USA, what they found was that actually there was quite a bit of underreporting by the EPA, the Environmental Protection Agency, and EDGAR emission inventory by about 50%, specifically in the southeast of USA and California. And this sort of underreporting was attributed to oil and gas and agriculture. And what was really nice about this study was that there were many other studies that actually confirmed some of these findings, particularly for California, in a similar way. And the second example, which I imagine Yogesh has shown you already, is for India. Of course, we know that India is a major methane hotspot for rice and ruminants. And in this study, again, here, GOSAT methane data was combined with inverse modeling for India. And what they found here was actually they had quite a good agreement with the national reporting to UNFCCC. And however, with the EDGAR inventory, they found that actually the emissions were too high. So this was actually a quite nice demonstration of how large uncertainties in our bottom-up inventories on country scales can be sort of diagnosed by using satellite observations. But of course, when you're using a satellite observation like GOSAT, because it's quite coarse, you really can only do studies, this kind of study on a large scale, so at country level. Right, so I'm just going to change course slightly and talk about sticking to certain emission sources. Because of course, if we want to try and understand country level greenhouse gas emissions, it's really important that we can monitor and then manage contributions from high emitting point sources. And we are now moving towards a sort of new class of satellites that allow us to go a step further and to actually target individual emission sources. So from the current suite of sensors that we have Sentinel-5 Tropomi, which is an image shown on the left-hand side here, and it measures on kilometre scales, and I will come back to Tropomi in a minute. But more recently, we've had the opportunity to bring together different satellite observing systems that can observe methane on different scales. And we've been specifically interested in hyper and multispectral instruments such as PRISMA, which is shown in the middle panel here. And this is a new Italian hyperspectral imager that we've been working with, as well as, of course, WorldView, which is a commercial multispectral instrument as shown on the right-hand side here. So with these sensors, they have quite coarse spectral resolution, only tens of nanometers, but they have meter scale spatial resolution. And when you're using these sorts of measurements to look at methane, we can observe enhancements that are incredibly large. However, these sort of different range of satellites all employ different methods of data analysis. So when we're using this sort of suite of instrumentation to look at point sources, a key challenge and where the uncertainty is how do you detect and define where the plume is? Once you found a way of mapping and detecting the plume region, you can convert this information to an overpass flux estimate from the total mass that is emitted. So this is quite an exciting new area, and then many new players appearing like Carbon Mapper, but I'm just going to show you a couple of examples using TROPOMI of how we've looked at point sources with Sentinel-5P TROPOMI. So a lot of you are obviously already aware, and probably a lot of people are already using Sentinel-5P, but this mission is a pre-operational mission that was launched as part of the European Copernicus program, and it's a precursor to the forthcoming atmospheric monitoring Sentinel-5 mission. So the TROPOMI has a spatial resolution that can be as high as 3 by 7 kilometers squared, and this helps us to sort of generate a more accurate separation of methane emissions from the regional background. There's a link to the data here if you're interested in using it. So as I mentioned before, we are seeing many more examples of the application of Sentinel-5P TROPOMI to map anthropogenic methane sources. And these can be things like looking at leakages from thermal power plants, oil refineries, coal mines, and also unregulated sources such as landfills and dumping grounds. So this is just a nice example showing TROPOMI observations over the Permian Basin. This is from a study by Zhang et al. And the Permian Basin is currently the largest oil producing basin in the United States. Ideally, you need sub-kilometer resolution to pinpoint individual plumes. However, there are now various methods that are being developed to trace individual methane plumes with TROPOMI, which can help us pinpoint sources in just a single TROPOMI overpass. A key challenge from a detection point of view is that we need to be able to the key challenge really is that the individual point source of methane can be quite weak, and therefore we need methods to be able to detect these instantaneous plumes that sometimes can be relatively small. They could only be about 1 kilometer in size, and they could be quite short-lived, maybe only last in the atmosphere for about an hour. So some of these methods that you can use to sort of trace and map some of these plumes have been summarized quite nicely in 2 papers here. This is Cusworth et al. And Varon et al. I have both given nice reviews of methods that are adopted by the research community to detect fine-scale methane point sources. Some of these methods include the Gaussian plume inversion, which looks for enhancements of methane along the direction that the plume travels by fitting a Gaussian plume model to the satellite columns. We, of course, have the cross-sectional flux method and another method called the integrated mass enhancement, which I'll just go through now very briefly. So the integrated mass enhancement method empirically infers and relates the methane source rate to the total plume mass that is detected downwind of a methane source. This method requires that the pixels that contain the plume enhancement are accurately isolated from the background concentration. And this method also requires an accurate representation of the wind speed and direction at the time that the measurement was made, because this helps us to capture the atmospheric dispersion of the plume at the time of the orbit overpass. So the method consists of a number of different steps. These include calculating the plume area and the plume size, as well as the column mass enhancement. We need to know something about the residence time of the methane plume in the atmosphere as well. Of course, if the plumes are relatively weak, sometimes it may be necessary to wind rotate a number of consecutive orbits to help bring out better some of the plume features. There are a few limitations with this method. It really requires that the local meteorology is well represented, because if it isn't, this could lead to large errors in the methane source rate, which of course can make things very challenging from a monitoring and maintenance and monitoring perspective. And this is, of course, if you want to do long-term monitoring of sources, methane sources such as landfill sites, it's really important to do this with high accuracy, because that's the only way you can support and implement corrective actions as and when needed. So I'm just going to show you a couple of case studies here. We've been working on landfill sites in particularly because we wanted to test the feasibility of detecting methane plumes originating from European landfill sites. Of course, we know that waste is quite an important but poorly understood contributor to the global methane emission. And landfill gas in particular is a natural byproduct of the decomposition of organic material that we have gathered in landfill sites. We get approximately 50% methane and 50% CO2 and some other non-methane organic compounds as part of these emissions. And estimating landfill emissions can be very challenging because they are often unregulated and they can sometimes be large. This can lead to large uncertainties in the reporting of methane emissions from some official sources. So this is why it's very important to focus efforts on active monitoring of these sites, such as landfills, from satellite observations. So here is one case study that we looked at, a particular landfill site in Madrid. So according to the European Pollutant Release and Transfer Registry, landfills are some of the largest methane emitters in Europe. And in this case study, we were interested in a very particular one located in the middle of the city, Madrid, in Spain, which was reported to have methane emissions of 12,000 tonnes per year in 2019. Because this emission was quite large, there was an expectation that the methane plumes resulting from this landfill would be sufficiently large, at least tens of kilometres, and therefore would be large enough to be captured by Tropomi. So we had a look at Tropomi data here. And here are just some examples of individual overpasses. The little pink box in the map, it defines the area, and in the middle of this box is a site. So what we did here, we analysed 2 years of Tropomi single orbit overpasses of methane data, and we extracted all the Tropomi methane concentrations around the site. We developed a method that allowed us to isolate the methane plumes from the landfill site using a sort of statistical outlier detection combined with a clustering technique. And this enabled us to pick out the pixels that were coming from the plumes close to the source location. We then extracted corresponding wind information using ECMWF era reanalysis data, and then we applied the integrated mass enhancement method. And what we found from our estimates, which are shown in this table in the sort of third column here, using individual Tropomi orbits, we actually found that our emissions for a range of these orbits were sometimes almost 10 times larger than those reported by the official statistics for this particular year. So this is some of the work that we've been doing at the moment in terms of our European studies. Of course, we can also look at India. And we know that it can be very difficult to estimate methane emissions from landfill sites because often they're not regulated and maintained or controlled. And we know that sometimes these landfill sites can be located quite close to very populated regions. And this, of course, as shown by all these media reports, can become a very serious and hazardous threat to human health and the environment. So we're actually interested in looking at a range of landfill sites across India and trying to estimate the emissions from these. And some of these are sites such as Ghazipur in Delhi, which is supposedly the largest landfill site in this region. So we've had a little look at this. I looked at some of the statistics from the GHG platform for India, just to look at what sort of methane emissions we have from some of these sites. So this table just shows Delhi and a few other regions, and we can see that as of 2015, which is the sort of middle column here, it was estimated that the methane emissions from Delhi municipal solid waste disposal from the waste sector was around 33 gigograms per year. For a comparison, I've included a few of the states, and we can see that we have a range of sort of methane emissions from the waste sector being reported from as low as 1.13 gigograms in Chandigarh to as high as 65 gigograms for Maharashtra. So I wanted to have a look at look at Delhi in particular. You know, if we want to estimate landfill emissions, what does Delhi look like from Tropomi? So here is just a very nice example taken from 2018 in March, and the shapefile here is plotted over it, so we can see that the arrow points to Delhi. We can see a little white dot, which is the Ghazipur region, and we can see this sort of nice plume originating from this area. So I've been studying some of this data, and I just want to show you a few more examples. So here are some of individual Tropomi overpasses over the Delhi region. And this was just taken within a 2-week period in 2018. And we can see that we consistently see these methane emissions being observed nearly continuously from the Gazipur region. We then had a go at looking at this region in more detail and applying the IME method. So what we did here was we extracted the per pixel wind information from our ECMWF reanalysis to have a look at the sort of prevailing wind direction and speed. And we can see it matches quite nicely with the travel direction that we're seeing for the plume. We applied the integrated mass enhancement method here to isolate the plume pixels to help us establish the emission source rate. So at the moment, I think we need to just review our methane emissions estimates for Gazipur region. And it's really important that we calculate the uncertainties and validate them first. So I'm not going to show you what I've calculated for the Gazipur region, but what I can say that it's quite a bit higher than those that have been reported by the GHG platform for India. And what I'm hoping is that I'll be able to work with some of my collaborators to review and understand these numbers. So hopefully next time I speak to you, I'll be able to show you some of these emission estimates. So just moving slightly before I summarise, we of course have new sensors like GHG-SAT, and it's really worth pointing that these commercial data providers like GHG-SAT have designed these satellites specifically to look at point source detection. So this is, really this is what their purpose is. And although it's a commercial satellite, there are ways to get hold of the data. And we've been able to get hold of some of this GHG-SAT data via the European Space Agency. And so they've been able to make some new measurements over the region, over the Delhi region for us. So hopefully next time I speak to you, we'll have had a chance to analyse some of this data, and maybe I'll be able to share some new insights about the point sources and landfill emissions from the Delhi regions from the GHG-SAT perspective. And with that, I just want to summarise. So hopefully I've been able to show you that satellites are providing us with ever more powerful carbon information across many different scales and domains. There are many new streams of information which have the capability to transform the field of carbon cycle research. And this really helps us to address key science questions on regional methane and carbon budgets, and also to gain some insights into the processes. Hopefully I've been able to show you that there are new opportunities and ways to tackle anthropogenic emissions, which will not only contribute to scientific understanding, but also help us support policy making and, of course, international treaties like the Paris Agreement. And I think it's really nice to show that there are many evolving methods around point source emission estimates, which show real promise. But this really depends on having a strong method to accurately separate plumes from the background. So hopefully I've shown you that there are many different opportunities to use different platforms and technologies. And really what we need to figure out is how to bring all of these things together to synergistically exploit and integrate these different observing systems. And with that, I'd just like to thank you for your time and attention.
Okay, thank you, Dr. Harjinder, for an excellent talk covering mostly a wider area, starting from carbon observations, from spaceborne observations, and in situ observations, and then particularly methane, and some highlights on this point source emissions from the Indian scenario. So we do have some questions, and I will read it to you. Some questions are from a student's point of view, very basic questions, and some are more on the particular aspects of your research. So one question I received from Vaishnavi Pandey asking, in which region of electromagnetic spectrum of the carbon dioxide is detected? As it is very challenging, can you comment on it? There's a question.
Yes, let me just show you. The region in particular is the shortwave infrared that we're focusing on, because the shortwave infrared region, let me just put that back into, let me just show you here. Yeah, it's a shortwave infrared region, 1.61 microns and 2.06 microns, which allows us to detect CO2 signatures. Of course, there are other observing methods like the thermal infrared, but the thermal infrared has sensitivity more towards a free troposphere. So if you wanted to look at near surface, you would use a shortwave infrared region.
Okay, thank you. And another question by Pravir is asking, could you please tell a bit more about the full physics and proxy retrievals of methane? Example, quality versus coverage, etc. So
Okay.
maybe our young participants may be curious of his comment.
So the full physics retrieval, it's mostly done. Oh, let me just see if I can do. Okay, this is probably the best slide. So the full physics is about, we need to do a Bayesian optimal estimation approach. And what we do basically here is you include a radiative transfer model that simulates the atmospheric spectra that you get from the satellite. So you have to make a lot of assumptions about some of the interfering species in the region of the spectra that you're looking at. You have to make some inferences about the surface and the atmospheric conditions at the time of the satellite overpass. So once you've made all of your assumptions and you've characterized properly the atmospheric spectra that you get from satellite, you simulate it, and then you use an optimal estimation approach. So basically this is, it's an iterative process, and basically you try to reduce the error and the difference between your simulation and your atmospheric spectra that you get from the satellite. And then from once you do that, I mean, it's quite, I could talk about it for hours, but you basically, then you calculate, then you are able to infer the sort of total column amount of your CO2 or your methane from your spectra, from your satellite. In the proxy retrieval, the proxy retrieval we use for methane only, and this is because we do a joint sort of retrieval of aerosol, and by proxy what you do is you retrieve the methane, but then you make some assumptions about CO2 and other parameters. And this is because once you can basically, by doing this sort of joint retrieval, you can normalize, and you can, the reason is because you have like scattering from aerosol. So you can sort of use a model amount and you can average out some of this information. Once you normalize your methane retrieval, you've sort of removed some of the contributions from aerosol and other things. So you have to use a little bit of additional information. The proxy retrieval works quite well, but it's not as involved. Oh, I can just show you here. Oh, let me just go back here. So it's not quite in the same way. So you use like a methane and CO2 ratio to cancel out some of these scattering from aerosol contributions that you can have in methane retrieval. So they're quite different approaches. The full physics is a lot more involved and line by line, and it can be quite time consuming. The proxy is slightly quicker.
Okay, thank you for explaining. And another question, actually, it's from my side. So this Anita's paper clearly shows the biases in the EDGAR emissions over India. And to note, actually, the same EDGAR data is utilized in one of the yesterday's talk by Dr. Atul to validate their model. And using that model, they further take the application to the food carbon, food-related carbon emission. So my question is that it appears that how satellite observations can improve the South Asian methane budget, and what is the current status on this subject? Can you please throw some light on it?
Sorry, was that how do surface observations?
No, the question is how the satellite observation of methane can improve the South Asian methane budget, and what is the status? Can you just elaborate on that a bit?
So in terms of the inversion modeling, it of course depends on how well constrained your initial modeling simulation is. And what we found in other areas, in other studies done with in collaboration with colleagues from Leeds and from Edinburgh and Bristol, is once you include your satellite observation as a sort of initial constraint, it just helps to to get the scale and the variability of your inverse modeling correct. And sometimes I think in Anita's paper, she'd used a combination of surface observations and satellites. So in terms of in the European European and UK community, I think there are some efforts to do similar studies over India. What would be really fantastic, I think, is just to have more. First, I think, is just have more surface observations across different areas in India, so that they can also be implemented with the satellite observation. And then when we use those two combined, you can then do an inverse modeling, basically similar to what Anita has done here. So I think the satellites, yes, they are really important to use with models, because it's the only way we're going to understand something about the emissions. But the satellite observations still need a little bit of help from surface measurements in some areas. And I think in terms of the states from India, it would just be fantastic to have lots and lots of more surface observation networks. And I think Yogesh, for instance, is already involved in some of these. And Yogesh and Pillai are now already involved in some of these new projects that will allow this to happen.
Yeah, that's exactly that. Last 2 days, we spent a lot of time discussing on expanding more observations, and we do have a few more stations of methane observations in India. Hopefully, that will be beneficial for future inverse budget estimates, I guess. And another question Pravir asking is that let me read. So the integrated mass enhancement method sounds like very good for hotspot emission estimation. So my question is about what's the result of the Madrid landfall emission. An order of magnitude higher than inventory method is a large difference. What are your next steps? I think he's pointing to the Madrid landfill emission.
For the Madrid. So I think some of this work is still evolving. It's a really nice, the integrated mass enhancement. Yeah, it's a very nice way to just isolate these pixels. It's quite challenging, of course. You have to have very good information about the site that you're interested in. So you have to get your coordinates correct. You have to have very as accurate as possible local meteorological information. And there are obviously challenges with using this method. Sometimes it doesn't. So, for instance, a cross-sectional flux method is also just as good as the integrated mass enhancement method. But sometimes if your wind speeds are quite low, you might end up with larger errors in your source rate calculation. So you have to apply this method in a very site-specific way, and it has to be quite targeted to the region that you're looking at. In terms of the next steps, I think we're still, so with this Madrid site, for instance, this was part of a commercial partnership that we had with a landfill company. And what we want to be able to do here is, the next step for this is really to have this in some near real-time way that you can constantly be looking at these emissions, and then you can then work with the landfill companies to start trying to do corrective measures, because I think that's what we need here in this particular case. And it'd be really fantastic if we could do this for a range of landfill sites over India, and as well as coal mines and other places. So the method has a lot of promise, and I think really the next step is the corrective measures and the maintaining and trying to stop some of these emissions.
Okay, Prabir, do you want to add more to this
question? No, thanks. Fantastic. This is also I'm curious. You also mentioned about this low wind and high wind conditions. So wind speed dependence. I think that's what also I wanted to know actually a little bit, and really mention that. I think it's fantastic. Thank you very much.
Okay, so the one last question perhaps for this session is the one Ankit Swaraj asking: methane tropomy is column average data. How do you estimate to ground level using IME? Actually, I don't also understand the question well. So I read it again. Methane propomi is column average data. How do you estimate to ground level using IME?
It's because although it is total column, if you look at because it's in the shortwave infrared, when you look at when you're looking at the retrieval parameters, you look at something called the averaging kernel, and the averaging kernel tells you something about the sensitivity of that measurement. And as I mentioned before, because we're looking in the shortwave infrared, most of that information comes from near the surface, and the averaging kernels show that most of the sensitivity of this kind of retrieval is near the surface. So what you sort of assume is that most of this information, yes, is coming from near the surface, near the sources that we're interested in looking at.
Okay, thank you. And any other questions for Dr. Harjinder?
Just I want to add a little bit on that, like the surface versus column. I mean, one of the behavior, I mean, for the students is that even though it is column, so when it is localized, you see that it's a hot spot, right? So as you understand, the wind speed actually increases very fast with height. So when you go, and these are long-lived gases, right? When you go up in the height, the wind speed is stronger and no emissions. So basically you have a layer which is very smooth and it extends over kilometers and thousands of kilometers. But near the surface, what you see here is like an order of 10 kilometers or 1 kilometer. And this kind of conditions actually only can happen at the surface. We don't see a methane plume at 10 kilometer or 5 kilometer height. It's impossible to have this kind of localized methane plumes. So there are a lot of intelligent thing goes on with this, what Harjinder showed. I mean, that's why she also mentioned like you need to know the location of the emission hotspot and so many other things. So you need a expert knowledge to make use of these data sets in a right way. So think about it when you design your research, and take help from these people who are like already doing it and has expertise. This is the whole idea of this workshop, right? So yeah.
Right.
Is that right?
Yes, absolutely. That's why the local meteorology is very important to get right in this particular case, sort of application.
Okay. Okay, so if no other questions, I would thank Dr. Harjinder for sharing her valuable time and giving an excellent speech in this workshop. Thank you very much, Harjinder.
Thank you.
And say thanks to Dr. Harmut also from regards from our side. Okay, thank you.
Thank you.
So we have come to the end of the plenary as well as keynote today, and now we will split into two groups like last 2 days. So please use the link of MS Teams for joining the training session. So I request all the trainees here, all the participants to move to the training session. Today there will be training on from training for transport modeling using particle trajectories and surface enhancement calculations. So I request all the participants to move on to your link number 2, training link, and panel members may remain. So I had today, Prabir, shall we take a 5-minute break before starting the panel discussions today?
Yes, yeah, you can take, and Harjinder, if you are around, if you want to stay on, you can stay on, but if you want to leave, I think we'll not stop you.
It'd be nice to, yeah, that's okay. I might just listen if that's okay.
Okay.
Thanks. Yeah, of course. I mean, of course, you are. I think you should then comment too, like on.
Yes. Okay.
Yeah. Yes. And as long as you want to stay, you stay, and you can leave anytime.
Okay.
Free. Thank you. Thank you.
So let me explain the background a bit when other members join. So today and tomorrow's panel discussion is for the basically on the inverse modeling aspect on a regional scale. And I have invited several different set of people for this panel discussion and tomorrow's as compared to yesterday and the day before. So I will be I'll wait for them to join. It might take some time. So we will start maybe in another 3 minutes, perhaps.